Hello again everyone, welcome back to ptet.chemistry channel. So in this new format of restructured tutorials, you will know that I no longer show the question paper. So for instance, this is the November 2020. This is the 9701 for the November 2020 paper. This is paper 4, not 42, 41. Alright, so I trust you know where to get your own question paper without me telling you what is the question paper or where's the question paper. That's the only way to circumvent all these unnecessary hassle about the copyright stuff. Okay, anyway, so what I do is still pretty much the same. Assuming you have the question paper in front of you, you will probably understand that the questions that I'm going through as I think out loud and explain the concepts. Right, before I start, do click the button on the bottom right if you have benefited from my channel, if you found the rest of my videos useful. So do subscribe to the channel, click the button on the bottom right to do that, and share the channel widely with everyone else you think who might find the channel useful. Follow me at ptet.chemistry on Facebook, Instagram, and Twitter to get connected and to send in messages or questions. Alright, let's get started. This is question number 1. You are given this equilibrium 2NO gas plus O2 gas going to 2NO2 gas. So this is a reversible reaction, it's in equilibrium, and you are told that the rate is equal to K NO square, and O2 without any square, it just means to the power of 1. So this is what you call a rate equation. A rate equation basically shows or expresses rate in terms of rate constant as well as the concentration of the specific reactant. So that is what you call rate constant. And then the power to which you must raise the concentration of each of the reactant, that is called the order, and this is order with respect to the concentration of NO, whereas this order, which is not shown here, it cannot be 0 and it doesn't show any number, it means it's to the power of 1, and that is the order with respect to the concentration of O2. So completing the following table, so it's got to be order with respect to NO is going to be 2, order with respect to O2 is going to be 1. So order with respect to NO is going to be 2 based on the rate equation, which you can read straight from it, and that is why the whole of this question is just worth 1 mark. And they want the overall order. Overall order is going to be the individual order sum up together. So overall order is going to be 2 plus 1, which is equal to 3. Now to the next part of the experiments, part B. You have 2 separate experiments. It's better if I actually copy down the data because it makes more sense if I actually have the data in front of me. Okay, I try not to do this too often because I don't want to be infringing any copyright stuff again, but it's necessary in this case because the data is given like this and I am not showing their question. I am simply writing out some values. All right, so yeah, don't blame me on that. Anyway, so these are data and they want you to use the data for experiment 1. So if you look at part 1, they say use data from experiment 1. So when you read this kind of question, you really have to try and circle and underline important parts of the question, and you got to use that value for experiment 1 to calculate rate constant, and also calculate rate constant as well as state its unit. So in question where they don't ask you to state the unit, it's good to practice good bookkeeping and just try to see if you can get the unit anyway. Alright, so unit of rate constant doesn't exactly mean a lot of things. If I just rearrange my equation, so my equation show me this, and that. If I move all of these down there, it's going to be rate divided by the concentration of this square divided by this as well. So K equal to rate over the concentration of NO square, NO2 to the power 1. Put in all the value from experiment 1. Okay, so 1.51 times 10 to the minus 4 divided by 0.00300. Don't forget to square that on your calculator. Alright, and then on the other end, I will have mole per dm cube per second. That's the unit for rate. And then at the bottom, I'll have mole per dm cube square as well as mole per dm cube. I've always make it a habit of mine not to expand anything unnecessarily. In fact, what I'll do is I'll just write down as it is, and then hopefully then you can see that the mole per dn cube and the mole per dn cube cancel out. If I do if I do expand the whole thing out, I'll be doing unnecessary mathematics. I might make mistakes, and I might actually spend a bit more time on that rather than focusing on the more important stuff. Okay, so what happened that is k is equal to 8388.89, and in the AS syllabus in topic 1 under calculations, they don't specify as part of the lesson objective, but they say candidates in all manners of calculation, in all your calculations going from paper 1 all the way to paper 5. Okay, as long as you have calculations, you got to think about what is appropriate number of significant figure based on the data given. The data given was to 3 sig fig. Alright, so you gotta give your final answer to 3 sig fig to be appropriate number of significant figure. So there's your final answer to 3 sig fig, and our units based on these will be mole minus 2 because it's 1 over that square, and then dm to the power plus 6, and second minus 1. Now if we move on to the next part of the question, so this is B part 2. You want to calculate the value of NO concentration in experiment 2. So you want in experiment 2. There are two ways of doing this. I can think about one way is you use your red constant equation, red constant value, and then you put in red for experiment 2, and this is your unknown, and this is your known, and you know the K from the previous part of the question, and you can find NO concentration. So let me just try that first and show you what is going on. So remember, red is equal to K NO square and O2. You don't want to be wasting too much time on this kind of question. Really, it should be straightforward. If I just rearrange my equation first, then red over K and O2, and if you're able to do one step faster, you will see that when you remove the square root, when you remove the square, it will become square root on the other side, and you want the data for experiment 2. So what I could do is I could just plug in my rate for experiment 2, which is 6.05 times 10 to the minus 5 divided by the red constant, which I gotten in the previous question. I want to try and use the more exact value, which was 8388.89. And then the concentration of O2 from that experiment 2 was 0.00500. Okay, don't forget that you do want to do everything in this in that bracket first before you actually do the square root. So let me just, okay, so I get 1.442 times 10 to the minus 6, and then I'll square root that. So NO concentration give me 1.20099 times 10 to the minus 3. Of course, the 3 significant figure to be consistent as well as appropriate number of significant figure based on the data given, and this is concentration, so it will have a unit of concentration. All right, another way of doing this, I'll show you another way. I'm not too sure whether you like this other way or not. This is using the ratio method. The ratio method would mean that you skip the idea of red constant, because you never know, you can never be too sure that you have not done any mistake in the red constant, although I'm quite sure that you wouldn't make a mistake in a simple calculation like this. If you want to score very well for paper 4, you shouldn't make any mistake at all. All right, so I'll show you the idea of using the ratio method. Both methods will give you the same answer. So if you use red 2 over red 1, this is ratio method. So you're going to have K and then the NO square and then the 0.00500. So I'm keying in all the information from the red equation based on each of the experiment. Alright, so this is the data for experiment 1, and this is a red constant times the concentration of NO square times the concentration of O2. This is my only unknown, and I can equate that to the information on the rate from the data given. Then all I have to do is I have to just find NO square, and K will cancel, and then you can get the exact same answer. So NO square is going to be 6.05 times 10 to the, basically it's the same thing on the other side, and you're just doing a big rearrangement exercise. Yeah, it's just a bit tedious really, but I mean, once you set it up, all right, at least you skip the step of finding or using the red constant, but it's really a matter of preference. Whichever method you use, do not forget that this is square equal to all of these, and when you want the one without the square, then you have to square root the whole thing, and you will get the exact same answer as 1.20 times 10 to the minus 3 mole per dm cube. If you round it up to 3 significant figure, which is the appropriate number of significant figure based on what the question wants. All right. So question 1, part C, define rate determining step. So rate determining step, well, I don't know why I'm repeating the question. I should go straight to it. Rate determining step is the slowest step in the overall reaction. So this is a key 1 mark question. So slowest step in the overall reaction. And what is important also is whatever reactants is involved in it, whatever reactants that are involved in the rate determining step will have its concentration appear in the rate equation. Okay, so whatever they appear in the rate equation means that those reactants will affect the rate of reaction because they are part of the slowest step or the rate determining step of the reaction. Alright, so moving on to the next part of the question. So we have a case study. This case study comes under rate of reaction as part of catalysis. So the peroxide disulfate is H2O8 minus. And this reaction can be catalyzed by iron 2 homogeneous catalysis. As you can imagine, this is a negative charge and negative charge. The reaction is going to be slow between these two ions because they have high activation energy. Since they repel, okay, same charges will repel, same charges, therefore repel. Slow reaction, slow reaction. Now, if you have a two-step mechanism, based on this thing, they give you the rate equation, H2O8 minus and I minus. We look at the rate equation given and we see that this is first order with respect to S2O8 minus. And we also notice that despite the equation showing you 2I minus, the rate equation shows you that it's only first order with respect to I minus. So what in the world is going on? They say suggest equations for a two-step mechanism. And then which one is the rate determining step? So we know it's a two-step mechanism. It doesn't go straightforward because, well, it's not two of them in the same step. Okay, so it's not like one of these and two of these in the same single step reaction. So perhaps in our first reaction, they have to collide. So if I have that and that, what can it form? Well, we know that the SO42 minus has to be formed from the S2O8 minus. So I gotta get SO42 minus. But the question is, what else can I produce? If I produce two of that there, then what will happen to the I2? I mean, I will just get straight to the product. But I want to proceed via a two-step mechanism. I need an intermediate. I need something else which is not the product itself. Otherwise, there's no point of doing two-step mechanism. You could just get to the final product yourself, all right? So instead of forming two of these, I'll just form one of these. And then that means I have another SO4. Okay, so the SO4 come from S2O8 minus. I will have SO4, and then I'll have an I. The question now is, this is a 2 minus and this is a 2 minus. I must have a minus charge there. So this intermediate does not make any sense at all, but it does not matter because it's an intermediate, and intermediate can react further with the other reactant. That's why you have 2I minus overall. But in your rate determining step, in your slow step, you only have one of these and one of that. So this has got to be your slow step, and this is your rate determining step, meaning step 1 is your rate determining step. Moving on to the next part, which is the intermediate reacting with I minus. It will then give you SO42 minus, and then it kick out the I plus there essentially and give you the I2. So what actually happened then is we can see overall we have 2I minus because when you add this and this together, this and this will cancel out because they're on opposite side of the equation, and you have 2I minus and you have 1I2 and 2SO42 minus. So this intermediate is generated as part of the multi-step reaction, and then the intermediate further reacts to give you the product. So very clearly, your rate determining step is going to be step 1, because you only have one of these and one of these react as per the red equation there. All right. So in the next part of the question, so they say a large excess of the peroxyl disulfide ion mixed with iodide ions. If you have a large excess of it, the concentration of S2 or A2 minus is going to be constant, because it's present in a large excess that using some of it is not going to change much of its concentration at all. So that means we're just looking at how the iodide concentration falls over time. We can imagine this as the iodine concentration, not the iodine, the iodide concentration, which is our reactant. Our reactant is iodide. So what happened with the iodide concentration? At T equal to 0, and then half that initial concentration. When you halve the initial concentration, the time taken for it, which is the half-life, is 48 seconds. And then we know it's first order because it's first order with respect to I minus. When this is in large excess, your rate is roughly equal to rate constant times this. So it's first order with respect to I minus. Since it is first order with respect to I minus, therefore half-life is constant. If you have constant half-life, that means your second half-life is going to be exactly the same as your first half-life. So another 48 seconds, you will get to 1/4 the initial concentration. And then there's 48 plus 48, that is 96 seconds. Is it? 48 plus 48, 96 seconds, and it's still not 192. So you keep on going for another 48 seconds, and you get 1/8 of the I minus T equal to 0. So 96 plus 48 is still not 192, or whatever number they want there. So I need to try and do one more, and then I'll get half of that. 1/8 is 116, I minus T equal to 0. So there's another 48 seconds. So altogether, what I've done is 1, 2, 3, and 4 half-life. After 4 half-life, then I will have reached the 192 seconds. So calculate the iodide concentration, 192 seconds. So after 192 seconds, there is 4 half-life. So essentially what happened is you can think about 4 half-life, which is 1/16, times the initial iodide concentration, which is 0.00780. 1/16, or 1 divided by 16 times 0.00780. I get 4.875 times 10 to the minus 4. Run it up to 3 significant figure as per the data given in this particular question, and you will get this as your final answer to 3 significant figure. Hope it makes sense there in terms of why the half-life is constant, because of the overall order being first order with respect to I minus, and the concentration of this being constant means that the overall order roughly is first order with respect to I minus, and therefore you get a constant half-life, which is the same half-life whether you go to the first, the second, the third, the fourth, and they just keep on halving the initial concentration more and more and more. All right, so that's the end of that 8-mark question there, and we should move on to the next question, otherwise we'll run out of time in this paper 4. In this next question, question 2 is about lattice energy. So they started out by giving you this compound, which is LiF, and calcium oxide and strontium oxide. So the lattice energy is expressed as kilojoule per mole. As you will notice, they are all exothermic. So 1022 minus, and 13513 and 3310. Okay, so they want you to define the term lattice energy for 2 marks. You will realize that a lot of Cambridge questions starts off by asking you to define something. So you should have really prepared for definitions, everything from AS definition to A2 definition, all right? So lattice energy is basically the enthalpy change when one mole of ionic solid is formed from its gaseous ions Okay, 1 mole of the ionic solid or 1 mole of the ionic lattice, whichever one you like, is formed from its gaseous ions under standard conditions. The standard condition should be written down as well. So whether you like 25 degrees Celsius or 298 Kelvin, and whether you like 1 atm pressure, or you can write down 10 to the 100 kilopascal, whichever one you like. On to the next one. They are saying that why the lattice energy of calcium oxide more exo. More exo means more negative than the lattice enthalpy of LIF. To understand that, you really must understand that what is to do with lattice enthalpy. If you think about lattice enthalpy, you are forming the ionic lattice from its gaseous ion. So we are forming ionic bonds. So how strong is your ionic bond? Okay, so basically, how strong is the ionic bond that you are forming? How strong is the ionic bond being formed? These are factors affecting the strength of ionic bonds. You got to think about charge, and you got to think about size, which is to do with ionic radius. And each of these will affect cations, so as well as anions, and size as well, because you have ionic radius of cations and you also have ionic radius of anions. Essentially, the charge and the size are expressed in terms of charge density, because charge over volume is going to be charge density. So we can be thinking about the calcium oxide consists of calcium 2 plus and O2 minus. This is Li plus and F minus. Yes, F minus is smaller than O2 minus. And is it? Well, let me think. What do you have? You have F and O. We know that F is smaller than O, but this is proton 8 and 9, electron is 10 and 10. So the fact that you have more protons and attracting more electrons, so your size of F minus is going to be smaller than O2 minus. All right, so very clearly this O2 minus and F minus. As you know from your AS anyway, that atomic radius decreases across a period. So this is atomic radius. So this is size or radius. And of course, then you also have the ionic radius of cation. Ionic radius of cation is smaller than the parent atom, but the ionic radius of anion is bigger than the parent atom, but still the trend decreases. So if you have O2 minus there, F minus will be there, for example, all right? Of course, the usual trend they ask for is the atomic radius or ionic radius across the third period, but it's periodicity, so the same trend is repeated in the second period, the same as the third period. Well, anyway, going back to the focus of the question. The focus of the question was on why the lattice is more exo than the lattice of lithium fluoride. So I can be thinking about the charges on the cations, okay? So calcium 2 plus has plus 2 charge versus Li plus has plus 1 charge. This is charge of the cation. Okay, very, very straightforward. O2 minus has minus 2 charge, whereas or versus F minus has minus 1 charge. So here you got to think about which one is the dominant factor. Okay, yes, there are two factors that can affect the value of lattice energy as well as the strength of the ionic bond, but what is very important is you always focus on which one is the more dominant factor. That will help you to explain the idea here. Okay, so therefore calcium 2 plus and O2 minus forms stronger ionic bond, and the stronger the ionic bond that you are forming in the lattice, therefore you are more exothermic, so then LiF, all right, then Li plus and F minus. Okay, so I've talked about two things there. There should be enough for that 1 mark, I guess. On to the next part of the question. So question 2a part 3. They say use data in the table to estimate. These are the kind of questions that a lot of students don't like because they don't have an answer. All right. In this kind of question, do not be afraid. It's more about suggest or based on the data given, try to think about what is what. All right. So let's think about it. Calcium oxide is minus 3513 from the table. Strontium oxide is around minus 3310. Then how about the other thing they want you to suggest? They want you to suggest for barium oxide as well as magnesium oxide. We know that going this way, Going this way, the radius of M2 plus, the group 2 cation, is getting bigger, therefore weaker ionic bond, or I should say lower charge density first of all, because charge density is charge over volume. So your charge of the group 2 cation is always the same, plus 2, but then the size is getting bigger, so this is a weaker ionic bond. So since this is a suggestive kind of question, we can see that there's a difference of around 200 there. So if the difference is around 200 there, and this is immediately down the series, I would not even hesitate to even think about, you know, like minus 3,500, minus 3,000, oops, sorry, not, it's going to be less exothermic because it's a weaker ionic bond. So I don't know, minus 3,000, minus 3,100. Somewhere along that line of a difference of 200, I think that would be alright, because it's just a suggestive question. As long as you got them the right way trend around, meaning stronger ionic bond, more exothermic, I don't think it would be too far-fetched to think that this would be roughly around that region. So give or take, you know. So if you want, you can minus 3,100. If you don't want, minus 3,000 would be alright as well, I think. Okay. Alright, so I mean there's just a 1 mark suggestive question. Moving on to the next part of the question. So you have B part 1. You want to write the equation between barium oxide as well as water, and they say it includes that symbol. So this is solid and this is liquid. Barium hydroxide is very soluble in water because it's very, very alkaline as a result of its high solubility in water. It's dissolved in water, that's why it's aqueous. So yeah, this is a balanced equation already. Okay. So the next part is actually a fixed essay kind of thing. It's a 4-mark thing where they want you to state and explain the solubility of the group 2 hydroxide. I gotta see how much space I have here. Perhaps I don't have enough space down there, so what I'll do is I'll just do it on a new page, because it's actually an important essay that always come out. You just don't know which one is going to come out on. Okay, so we're going to think about the solubility of the group 2 hydroxide. So MOH twice. All right, so this is the solid. We are going to try and dissolve it in water such that we get M2 plus aqueous plus 2OH minus aqueous. Alright, so what happened then is I will try and relate in my lattice enthalpy, which is M2 plus gas plus 2OH minus gas. This is forming the ionic lattice, so this is going to be the lattice energy. This is dissolving, well, not really dissolving, but taking 1 mole of the gaseous ion and surrounding with a large volume of water. This is the hydration. Hydration of the cation is going to be exothermic. In fact, hydration of the anion is also exothermic, but hydration is for 1 mole of the gaseous ion. I have 2 mole of the gaseous ion, so it's actually multiplied by 2. In terms of your Hess cycle, hopefully you can see the enthalpy of solution is going to be equal to going this way. So what I have then is enthalpy of solution is equal to minus the lattice enthalpy plus the hydration enthalpy of the cation plus 2 times the hydration enthalpy of the OH minus. Going down group 2, so what happened down group 2 then? Alright, so I know they asked for state and explain, so I still need to state something towards the end. Either you state first, or either you go to the very end and then you state the trend itself, or you could simply state the trend from the very beginning. We know that the solubility of the group 2 hydroxide with the general formula M2 plus OH minus, so you need 2 of that OH minus to get an overall compound which has no charge. So it becomes more soluble down group 2, so it increases down group 2, it becomes more soluble, and that's why it's more alkaline. If you think about the alkalinity or the basicity of the group 2 hydroxide, we know that magnesium hydroxide is not very soluble. So if magnesium hydroxide is not very soluble, because when you dissolve magnesium oxide, which is a period 3 oxide, MgO, a case study from AS period 3 chemistry, and that's going to dissolve in water to give you pH 9 because it dissolves partially, or it dissociates partially into OH minus. It's not very soluble. On the other hand, if you have barium hydroxide, barium hydroxide that comes from barium oxide in the previous part of the question. So it will give you barium hydroxide, which is very soluble in water, and that's why it will give you a very high pH as a result of like full dissociation into OH minus in water. So we're ready to go on to our essay. In terms of our explanation, we already have our equation from our hair cycle, very basic hair cycle that I have drawn earlier. So down group 2, how can we address this? All right, so there are more filled electron shells. So some of these assays, they come in different derivative. They come in different variations. It really depends on how you want to write it, but the main essence of the concepts remain the same. That is to do with the metal cations getting bigger in size. So metal cation getting bigger in size. I'm going to talk about bigger ionic radius, bigger in size, but the same charge. So it's the same +2 charge because they are all group 2 cations. So charge density of the cation, so charge density, which is equal to charge over volume, it will decreases down group 2 because all of these is talking about down group 2. Alright, so as charge density of the M2 plus decreases, my hydration enthalpy of the cation, not just hydration, because you have hydration of the the hydroxide, which doesn't change as you go down the group 2 hydroxide, but this one will change and this will change. These two are affected by the charge density of the cation. So the hydration enthalpy of the cations and also the lattice enthalpy of the MOH twice becomes less exothermic because, well, the cation is getting bigger despite the charge being the same. So as a result, the charge density decreasing. That will be a common thing that happens as you go down group 2. However, we know that it become more soluble down group 2. It become more soluble down group 2. So this thing has to become less endothermic or more exothermic. All right. So we know as a result of the trend. So overall, delta H solution of the group 2 hydroxide, it become more exothermic going down group 2 as it become more and more soluble. I can think about it in terms of less endothermic as well. Both things are saying the same thing. They are moving the same direction in that sense. Because this is the most important one. Because this is the one that will be totally opposite if you are talking about solubility of sulfate as a result of considering what actually happened going down group 2. Alright, so this is where I will spend a couple of minutes explaining what is going on here. So this thing is lesser than 0. It's exothermic. By definition, you are forming the ionic lattice, that's why it's exothermic. By definition, you take 1 mole of the gaseous cation and you surround it with water molecule and you will form ion dipole bond, ion, and the dipole from the water. So the water surround the cation, the gaseous cations, and they become hydrated, they become aqueous cations. So it's going to be exothermic without any without anything to consider. I mean, it's just hydration of cation, hydration of anion. Similarly, remember that the water molecule, it has got dipole, it's got delta plus and delta minus. So the opposite dipoles will attract depending on whether you have cations or anion. As a result of the negative value, but you have a negative, so overall this will become positive. You have a negative, but this is a plus negative. Overall, this will become negative. So what we are saying is down group 2, this thing doesn't change because they are all group 2 hydroxide. So even though I have written this down, I don't care too much about it. I want to care about these more. I want the overall enthalpy of solution to become less endothermic and more exothermic because I want it to be more soluble. I want it to be more exothermic or less endothermic down group 2 for the hydroxides. Okay, so if I want it to be more exo, if I want it to be more exo overall, I want this value to be bigger than this because this is the negative component. I want it to be more exo. If you want it to be more exo, I want this to be bigger than this. So even though both of them are decreasing, this must decrease lesser because I want this to be a bigger value so that I will get overall more negative. If this decrease lesser, this will be a bigger value. If this is a bigger value, it will give me more exothermic enthalpy of solution going down to group 2 hydroxide. Now let's work backward. I want my enthalpy of solution for the group 2 hydroxide to become more exothermic or less endothermic as a result of the solubility of the hydroxide increasing. I want it to be more exo. So I want this value to be bigger than this value, and therefore since I want this value to be bigger, I cannot let it decrease more. It must decrease lesser than this value. Alright, so the decrease in the hydration of cation is lesser than the decrease in lattice enthalpy there, because the decrease in the hydration of the cation is lesser than the decrease in lattice enthalpy or lattice energy. So that is how I explain it. I mean, there will be similar variation. You could be talking about decrease in lattice is more than the decrease in hydration of the cations, and as a result, the enthalpy of solution become more exo and less endo. Obviously, when you're talking about the solubility of sulfate, we know the sulfate of the group 2 become less soluble than group 2. So we're going to be talking about the opposite trend in order to get the opposite trend for the enthalpy of solution, in order to get the opposite trend for the solubility of group 2 hydroxide. Okay, so those are all covered actually in my A-level concept tutorial videos, which I never deleted, and you just have to look for that playlist on my channel along with other great A-level tutorial concept videos as well. All right, so let's move on to the next part of the question. So question 2, part C, this is about lattice energy and Born-Haber cycle. You might find it helpful to construct energy cycle. So realistically speaking, you have to construct a Born-Haber cycle, otherwise it's difficult for you to keep track of what is going on. So they have given you the blank space, so we don't really have to consider exo or endo. You can do an energy cycle where going up is endo and going down is exo. Personally, I like the freedom given by this question because I get to do what I want to do. So let me get started by writing Mg solid plus, so what do I want? I want my MgF2 solid. So this is my 1 mole of the substance formed from its element. So this is F2 gas, fluorine as a gas, diatomic gas. You know that from your O-level or IGCSE chemistry as part of your covalent bonding. The group 7 atom would form a covalent bond, single covalent bond with another group 2 atom. So that is going to be your formation of MgF2. And you know about all these definition from your AS energetics. Anything from AS can and will be asked in A2. Alright, so the first thing you do is you try and atomize the thing. You form 1 mole of gaseous atom from its element in the standard state. This is going to be atomization of Mg. Multiply by 1 because you're only forming 1 mole of the gaseous atom. On the other hand, you must have 1 mole of F2 because there's the stoichiometry to form 1 mole of MgF2. The substance is this ionic compound, Mg2 plus and 2F minus. So you have 2F gas, and from there you can obviously see this is 2 times the atomization of fluorine. Alright, but since both of these are in the gaseous state and you are not actually given the enthalpy of atomization of fluorine, alright, instead you're supposed to use the data booklet, and this is equal to 1 times the energy of the FF single bond, because with everything in the gaseous state, I'm breaking 1 mole of the covalent bond. Alright, this is equal to forming 2 times the gaseous atom from its element in its standard states. So these two relationships are the one that a lot of students couldn't get. They keep on trying to think about why is the question not giving us the atomization of fluorine, because you're supposed to relate it to the bond energy of the fluorine as given in the data booklet. Perhaps I should use the same color just to avoid confusion. So after that, I want to go to my first ionization energy, and then I can go to my second ionization energy of magnesium. So that is 1 times the first ionization energy of magnesium. They are all in your AS syllabus under atomic structure, the first 2 or 3 topic, the definition of which is defined as removal, the energy required to remove 1 mole of electrons from 1 mole of gaseous atom to form 1 mole of gaseous ion with a +1 charge. So all these are from your data booklet as well. So what do I do with this fluorine then? So I know that I need 2F minus gas. So what I do then is I don't have first and second electron affinity because I just gain one electron for every single gaseous atom. This is going to be 2 times the first electron affinity of fluorine, because the first electron affinity of fluorine is defined for 1 mole of the gaseous atom, gaining 1 mole of electrons to give you 1 mole of gaseous ion with a -1 charge. So you're forming 2 mole of it from 2 mole of these, so it's 2 times the first electron affinity of that. So the gaseous ion, okay, forming the ionic lattice, 1 mole of the ionic lattice, this is going to be lattice energy of that magnesium fluoride. And the job here really is calculate a value for this lattice enthalpy. Hope you can see that all of these are moving in the same direction, and this is equal to moving in this direction. Hess law in AS says the enthalpy change of a reaction is independent of the pathway you take, as long as you start from the same reactant and end out the same product. So all of these are in the same direction. You can add them up. Is equal to this other direction. So what I can do is I can just, this plus this plus this plus this plus this plus this equal to plus that. So if I just do 1, 2, 3, and then this is 4, 5, 6, and 7. Hopefully you can see 1 plus 2. Well, I don't literally mean, the number itself. What I mean is the expression that I have labeled this thing is equal to this 7, which is the formation of MgF2. Your target is to make the lattice enthalpy the subject, because that's what you want to find. So really, I'll just put a big bracket on there. And what I can do now is just look at my values and see what I can put in. Alright, 1 is the atomization of magnesium. So what do I have? I have 1 time plus 147. 2 is the first ionization energy of magnesium, and 3 is the second ionization energy of magnesium. So straight away I can get that from the data booklet. And what is 4? 4 is the one that they didn't give me, but I know I'm forming 2 mole of the gaseous atom, and that is equal to 1 times the bond energy that is given in the data booklet. So I'm breaking 1 mole of the covalent bond. And 5 is 2 times the electron affinity, because I started with 2 mole of the gaseous atom, and I get 2 mole of the gaseous ion with a single -1 charge. So plus 2 times minus 348, and all that in the square bracket. 6 is going to be your lattice enthalpy, which is what I want, and 7 is going to be your formation of MgF2, which is given in the question equal to -1102. So what I do next is I just make that lattice as your subject, and then I have a minus because all of this is a plus. Then I just work out whatever is in the bracket and just press everything into your calculator. Because you're pressing calculator, make sure you press all of these and put it into this bracket here, and it's a minus the whole thing in the bracket because you move the whole thing to the other side. Instead of rewriting the formula, you can do your evaluation, your calculation, and put it in there, and you will get 1795. So pop that into your calculator. Overall, you get your lattice enthalpy to be -2897. So don't forget, in this kind of topic, especially to do energetics, enthalpy, entropy, and Gibbs, sign, value, as well as units. Even in your working already, be very, very careful, yeah? Sign, value, and unit. So as given in the question itself, they give you this thing and they give you empty space. They don't provide the unit in there. So you gotta have sign, value, and units as part of your final answer, because without the unit, it means nothing. Especially in your working already, if you don't have the unit, you will not make it a habit to actually write it down in the final answer space. So be very careful to get the 3 marks in full, yeah? So we're still on question 2. So question 2D part 1. They want you to define the term electron affinity. Remember that it's a lot easier to define ionization energy or electron affinity in terms of writing equation. Write an equation and then you can see what's going on. Be careful, this kind of equation, electron affinity or ionization energy, they have particular stat symbols. So very, very careful, yeah? So electron affinity, refers to the enthalpy change. In fact, they should be asking on the first electroaffinity. I don't know why they're just saying electroaffinity in the context of this question. In the context of this question, we are just having the first electroaffinity because we stop here. I'm assuming that's what the question is asking me to do, because second electroaffinity will have a different meaning, obviously, all right? So it's the enthalpy change when 1 mole of a gaseous atom, look on the left-hand side above, 1 mole of gaseous atoms, what happened to it? It gains or accepts or receives 1 mole of electrons. And what does it form? It forms 1 mole of gaseous ion, or you can say gaseous anion, with a -1 charge. I never bother really with writing out singly or doubly or whatever. It's really up to you if you want to write all those things down, but it's very obvious that if this is a -1 charge, just write down what is obvious, and at least it will make your life easy without having to remember so many things. You're just writing equation, which you know how to do already from year 9, and of course you're just defining from the equation itself. There's the shortcut, at least as far as I'm concerned. Part 2 suggests an explanation for the difference in electron affinity. So we're looking at electroaffinity of fluorine versus carbon. So fluorine, as we know, is 1s2, 2s2, 2p5. Carbon is 1s2, 2s2, 2p2. So obviously this one wants to gain 1 electron more than that. And why is that? All right, so if you compare their first electron affinity, given in the data above, the first electron affinity of fluorine is -348 kilojoule per mole. This is all part of the question which you are analyzing. They are not part of your answer space. So that is -120 kilojoule per mole. So this one is not as favored. When I say favored, we are looking at as exothermic as possible. It means that it's favored. Okay, more exothermic, more favored. Of course, you will be able to relate these to Gibbs energy in terms of delta G equal to delta H minus T times delta S. If delta H is more negative, delta G is more negative, and therefore it's more favored, more feasible, more spontaneous. So it's better, it's preferred, all right? So of course you have done delta G as part of A2 chemistry. That's why I'm relating that to A2 chemistry in this particular regards here, okay, in terms of this particular formula. So what do we know? In terms of your answer, how would you answer it? Well, here's how I will answer it. I will write equation because that is what I do best. Plus electrons give me F minus gas versus carbon gas plus electrons give me carbon minus gas. So what can I say? Fluorine atom has more protons and also electrons than carbon atom. So we know that fluorine is actually smaller in size than carbon atom. So the effective nuclear charge, higher nuclear charge, perhaps I can say that first. More protons. I don't really want to remove that. More protons than carbon atom. So higher nuclear charge. So fluorine has higher nuclear charge. Okay, fluorine atom also has more electrons in the same shells. More electrons in the same shell. So shielding, which is roughly constant, overall effective or the net nuclear charge of fluorine atom is stronger or is higher. Higher, or you can use the word stronger than that of carbon atom. Therefore, fluorine atom likes to gain 1 electrons more than carbon. Essentially, we are saying that it prefers this more than carbon because it's more exothermic, and as a result of the higher effective nuclear charge due to more protons and more electrons, but they are in the same shell, so shielding is roughly constant, and therefore high effective nuclear charge. How do I know how to unlock this question? The basic essence, well, what do I say, the basic essence. The key really, I think for this question is to do with Z effective. You can think about electronegativity, but it's the same factor that come down to nuclear charge, shielding, as well as overall effective nuclear charge. So that's the end of their 15-mark question. This is question 2 for this paper 4. Question 3. So question 3 started out by talking about electrolysis. Question 3 is about electrolysis. So we have electrolysis of aqueous sodium sulfate. So if we identify the cation is Na+, we also have H+ from the water, and then the anion SO4 2- from the salt, as well as OH- from the water component, which is aqueous, meaning in water. And of course, you have done in A2 something about Kw. So it means that water does dissociate, but very, very reversibly, very, very small amount into H+ and OH-. That was why you have H+ and OH- whenever you have aqueous solution when you did electrolysis back in O-level or IGCSE chemistry. In terms of Na+ and H+, which one will get preferentially discharged? It will be H+ because they prefer reduction. As you think about the E0 value, the E0 value of this is going to be way more negative because sodium prefer to lose electrons a lot more than hydrogen itself, and therefore this is 0.00 volt relative to this. Well, this one relative to this one, this is 0.00 volt, and the E0 of Na plus Na is lesser than 0, whereas the E0 of H plus H2 is equal to 0.00. So this one prefer oxidation more than this. This will get preferentially discharged. Between the SO4 2- and the OH-, the OH- will get preferentially discharged because this one will prefer reduction, as the E0 is more positive. The E0 is more positive. And you have the data booklet to decide all these, or you can just use your O-level or IGCSE experience between the sulfates, the polyatomic ions, and the hydroxides. The hydroxide almost always get discharged because of their more positive E0 that prefer reduction. Prefer oxidation. What am I talking about? So it's actually more negative. I was wrong there, so it should be E0 more negative, prefer oxidation, because we know that E0 more negative, prefer oxidation. E0 more positive, prefer reduction. Reduction happen at the cathode, therefore oxidation at the anode. And we know that reduction is gain of electron. Reduction is gain of electrons, and oxidation is loss of electrons. These are just some of the usual acronyms that I use whenever I try to think about all these things. Obviously, the answer for this question is very straightforward. What is the product obtained at the anode? What's the product obtained at the cathode? You will not get the sodium metal at the cathode. Excuse me. You will not get the sodium metal at the cathode. Instead, what happened at the cathode is, the H plus electrons give you H2, balancing the equation. Done. The OH- will go to O2, and you will form H2O. You will get 2 of that, and you get 4 of that, and you get 4 electrons. And there's the half equation for what happened at the anode. A very, very popular question, not just from O-level at IGCSE, but it can ask you in A2 as well. Okay, so we know that this is the product obtained at the cathode, hydrogen gas, and O2 gas produced at the anode. So we do not produce oxygen atom, we produce oxygen gas. So you can write O2, or you can say oxygen. You can write H2, or you can say hydrogen. What you cannot write is, you cannot write oxygen just O. That would be wrong because that's not how oxygen exists at room temperature and pressure. Anyway, I spent enough time on that explanation. So jumping on to the next part of the question, this is a 4-mark question. It's a 4-mark question. This looks like it's the usual Q equal to IT, because we are given the time and we're given the current. So the first thing I will do is Q equal to IT. In Q equal to IT, Q is the charge, I is the current. Current must be in ampere, and the time must be in second. So a lot of students, when they do formulas, they just remember the formula, but without remembering the units, which are actually the essence of the underlying physics rather than the chemistry. So 4.50 ampere times 1.50 hours. Hours times 60 give you minutes, times another 60 give you second. So altogether is times 3,600 to convert hour to second. and put it into your calculator, and I can get 24,300 coulomb. The next part of the working is basically trying to relate what is Faraday constant. Faraday constant is basically 96,500 coulomb. Is the charge for 1 mole of electrons. I want to find out how many mole of electron actually passes through depending on the current that actually passes through. If I have 96,500 coulomb, it's a result of 1 mole of electrons passing through. If I have 24,300 coulomb, how many mole of electron is that? So this is the direct proportion kind of problem. So I'll just put it in, and the coulomb obviously cancel, and I get the mole of electrons. Put it into a calculator. I do not want to run up too early, and I come up to this answer that is to 5 significant figure, but it doesn't matter because we are not at the end of the working yet. I should probably find some space here if I write down part 3. They want the chlorine as well as the mass of sodium. I'm really running out of space here. Maybe it's better if I actually continue downward there. So I'll continue it in the next page. So question 3 B continuation. Yeah, okay. So just now there were 2 steps already. So step number 3, first of all, they want the chlorine. So this is molten sodium chloride. So that means you have Na plus and Cl minus only, because you have molten NaCl. There is no aqueous. Molten mean in liquid state. So you have Cl minus that will go to the anode. Oxidation happen at the anode, so you get that and that. So they want the volume of chlorine, and I know the mole of electrons that actually passes through based on the current that actually passes through. So 0.25181. 0.25181. Anyway, so this is why I like to express my mole ratio. So I set up the thing, I label this mole of chlorine, the gas that I want, over the mole of electrons, the information I have from my previous calculation. Then from my balance equation, I look at the mole ratio. 1 mole of Cl2 is to 2 mole of electrons. And then on the right side, I'll put in the actual number of mole. I said earlier, the mole of electron is 0.25181. And this one on top is about chlorine, and chlorine is a gas at room temperature and pressure. So I'll have volume of chlorine divided by 24. That means this is the molar volume of gas. If I use 24 dm cube per mole, that means this volume has to be in dm cube in order for the unit to cancel out. Doesn't matter, this is just something I'm telling you so that you will keep in mind your bookkeeping and your units. All right. So put that onto your calculator. So half times this times 24, I get an answer to be 3.02172 dm cube. And in fact, I should use 24. I just saw the unit given in the blank space for the answer. Volume of chlorine equal to blank space dm cube. So I use 24 dm cube per mole because this will be in dm cube. I do not want to have that many significant figure. Looking at the data given, just now the data given was 4.50 ampere. There was 1, 2, and 3 sig fig. 1.50 is 1, 2, and 3 sig fig. My final answer should be appropriate depending on the data given. So 3.02 dm cube of chlorine, 3 significant figure. Okay. The next part of the question is basically on the sodium. So the sodium ion will go to the cathode. Reduction happen at the cathode, and reduction is gaining electrons at the cathode. So the mole of sodium is to the mole of electron is just 1:1. From the balance equation, 1 mole of sodium come from 1 mole of electrons. In this kind of balance equation, in this kind of mole ratio setup, it doesn't matter if you got it the other way around, because if you got it the other way around, you're just reading the data based on what you have put down or what you have enter as part of your entry on the top bit and on the bottom bit. All right, so it's all matter of bookkeeping. Here on top, this is sodium. So I want the mass of sodium. If I want the mass, I have to think about MR, because not MR, I mean mass over AR or mass over MR. In this case, this is an element, so I need to talk about relative atomic mass straight from the periodic table. At the bottom, I have my mole of electrons that passes through, that come from my first bit of the calculations, working with Faraday constant as well as Q equal to IT calculation, 0.25181 mole of electrons. 0.25181 mole of electrons. So doing your cross multiply and your bookkeeping, hopefully you will come down to this and you will get this to be 5.79163. And of course, like I said for the previous part of the question, you want it to treat significant figure in order to reflect the data given in the question, which was 4.50 ampere as well as 1.50 hours. There was a three significant figure. This would be appropriate given the data in the question. So question 3, part C. The first part is drawing a diagram of the apparatus. So you want to measure E naught of the half cell. E naught of the half cell. So what do we need? We need a standard hydrogen electrode. Okay, and this half cell, we have MnO4 minus and we have Mn2 plus. So this is metal ion and metal ion. So remember, when you have metal ion and metal ion case study, you need platinum electrode. And the standard hydrogen electrode is the H plus and H2. This is a gas. So you gotta have 1 atmospheric pressure, 298 Kelvin. This is a solution, so 1.00 mole per dm cube. These are solutions, so 1.00 mole per dm cube of each in equimolar, in equal volume. So they are already in equal concentration, so you want to have equal volume. Okay, so we also need a high resistance voltmeter, obviously. So let's get started with drawing this setup. So what we have here is that we will have to draw a standard hydrogen electrode. It really does not matter whether we put our standard hydrogen electrode on the left or on the right, because the direction of electron flow depends on your E naught value eventually. So it doesn't matter where you put your standard hydrogen electrode, whether on the left or on the right. Your direction matters after you have drawn your diagram. If I just draw my setup with the standard hydrogen electrode on the left hand side, perhaps I'll have it a bit long, and then I'll have a tube, and this is three-dimensional with the hydrogen going into there. So the hydrogen comes in as a gas with 1 atmospheric pressure at 25 degrees Celsius, or you can choose at 298 Kelvin. And what we have is we must have a platinum electrode. If we don't have a platinum electrode, then on its own, hydrogen gas is not going to conduct electricity at all. And you got to have the electrolyte. Here is going to be 1.00 mole per dm cube. H plus aqueous, you could use like 1.00 mole per dm cube HCl or HNO3, but you can't use 1.00 mole per dm cube H2SO4 because there'll be 2 H plus per 1 mole in that 1 dm cube in that solution. Okay, so be very careful about what acid you can use. This is 1 mole per dm cube H plus. So on the other end, I would have MnO4 minus and Mn2 plus. Oops, I don't want an eraser, I want a pen. So what I'll have is I have equimolar, so 1 mole per dm cube MnO4 minus, and also 1.00 mole per dm cube Mn2 plus. So both of these are aqueous, so you want to mix them in equal volume. And because it's to do with metal ion and metal ion, I don't want that. Because it's to do with metal ion, what I really have to use is a platinum electrode as well. And both of these will be connected to across a high resistance voltmeter. So if I label these high resistance voltmeter, and I've got to complete the circuit because at the moment they are connected on this electrode to the high resistance voltmeter to the another electrode. I've got to complete the circuit by connecting across a salt bridge. And this salt bridge complete the circuit is usually made out of a soluble salt such as potassium nitrate or sodium nitrate. It's going to be spectator ion. It's not going to interfere with any of your reactions. They are just very soluble in water, and they allow the electricity, essentially the electrons, to move across the entire circuit. All right, I've got the standard conditions. I've got the electrodes, and it doesn't matter, as I said, whether the standard hydrogen electrode is on the left or on the right, because the direction of electron flow depends on your E naught value, as I mentioned earlier. So C part 2, this seems to be the end of the question, so the 11 mark question. So let's have a look at what they want. They want to say identify a substance. So they say identify a substance. You want to oxidize Mn2 plus to MnO4 minus under standard conditions. So we're looking at E naught value from the data booklet. So we know that the E naught of MnO4 minus and Mn2 plus, this is how we always write it. We write it in the form of reduction, and as you read from the data booklet, you will have the E naught having a value of plus 1.52 volt straight from your data booklet. So if you want to oxidize it, we are going to go against that way. So if we want to oxidize this Mn2 plus, be very careful of what the target is. The target is oxidize Mn2 plus. So essentially this one, we want it to be the EOX. If we want the reaction to be feasible, we need the E-ret, the substance that undergo reduction. The E-ret must be more positive than the EOX because we want the E cell, which is E-ret minus EOX. We want the E cell to be overall greater than 0 for it to be feasible and also spontaneous. So you got to choose something which is an oxidizing agent, because an oxidizing agent oxidizes the other substance and itself get reduced. So your E-ret has to be bigger than plus 1.52. I can think straight away of halogen from group 17 actually, as per your A-level curriculum, your A-level syllabus. We can be thinking about a really powerful oxidizing agent that's going to be fluorine. Actually, if I just have a look at the data booklet, if you have a look at the chlorine in alphabetical order, Cl2 going to Cl minus. So let me just write down somewhere. So E naught Cl to Cl minus versus the E naught F to F minus. So let's have a look at the Cl first. There's plus 1.36, whereas the F is plus 2.87. We have our EOX is plus 1.52 volt. So even though we say chlorine is pretty powerful as an oxidizing agent, it is not strong enough to oxidize this thing because it is less negative, it is less positive E naught compared to this. But this one can oxidize, the fluorine can oxidize Mn2 plus to MnO4 minus because this is more positive than this, all right? So if I write the overall equation, actually I will identify the substance first. So fluorine is very conveniently what we want, and you have 5 electrons in your half equations. If I just write it down somewhere, perhaps you can see it. So Mn2 plus 4H2O. I am reversing that equation. So you get MnO4 minus plus 8H plus 5 electrons. On your data booklet, it shows this going to this, but we know this is the oxidation step, so I have written it as such. And of course, then you have F2 plus 2 electrons going to 2F minus. If I just change all of these to a different color, so that it will be nice and easy to follow. Let's say green. Okay, so what we have here is 5 electrons and 2 electrons. We got to cancel out the electrons in order to combine them. So what we do is we have to multiply this by 2, not just the electrons, but the whole equation by 2. And we got to multiply this by 5, and then the 10 electrons on the left will cancel out the 10 electrons on the right, and you add up everything on the left equal to everything on the right hand side. So your overall equation is going to look like 5F2 plus 2Mn2 plus 8H2O, giving you 10F minus plus 2MnO4 minus plus 16H plus, and there's nothing on the left and on the right that can further cancel out. So this is going to be overall equation. They didn't ask you to explain why it's feasible, but if they do, then you can show the calculation. Your E-ret will be plus 2.87 minus bracket plus 1.52 volt, and you will get the E cell to be a positive value, which your calculator will not show you, because if it's positive, your calculator will not show you. So you got to write down the sign, the value, and the unit. And the sign of E cell being positive, as stated in the syllabus, is for a feasible and spontaneous reaction because the delta G will be lesser than 0. Okay,
That's the end of that 11 mark question on electrochemistry. Moving on to the next question. So question 4. Question 4a part 1 is a very straightforward question. They want the mathematical relationship. So without deliberating too much, straight away minus log to the base 10 square bracket for the concentration of H plus, and then Kw is the concentration of H plus multiplied by the concentration of OH minus. Taking into consideration that the concentration of water is constant because it's such a large value, and this is not Kc, this is Kw, representing water dissociation constant. So part 2, they want you to calculate the pH of NaOH. NaOH is a strong base. Because it's a strong base, it's going to dissociate completely into the OH minus, and that's why I can write a complete question like this. And they say this is 0.027 mole per dm cube. That means all of these come from these. If 1 mole of these, then you have 1 mole of Na plus and therefore 1 mole of OH minus. Therefore, your concentration of OH minus is going to be equal to the concentration of NaOH because of 1:1 mole ratio. All of these come from these. One of these give you one of that. And since they're in the same volume, if you have 0.027 mole in 1 dm cube, then you're going to have 0.027 mole of OH minus in 1 dm cube as well. So there you go, that is your concentration of OH minus. But then to relate that to Kw, so Kw is H plus time OH minus, and Kw is a value given in the data booklet as 1 times 10 to the minus 14 with a unit of mole square dm minus 6 because it's concentration times concentration. So your concentration of H plus is going to be 10 to the power minus 14. That thing is going to go down there, so you have 0.027 down there. And then last but not least, we know from our first expression in the first part of the question, pH equal to minus log 10 of H plus. So this particular answer from the previous part, you take the minus log 10 of it and press that onto your calculator, you get 12.431. They did not instruct us how many significant figure we should leave our final answer to, but looking at the data given in the question, the only numerical data given in the question is these. These are not counted as significant figure. This is 1 and 2 significant figure. As stated in topic 1 of your syllabus, in AS chemistry, they said that candidates should be able to appreciate what is appropriate number of significant figure. So what is considered appropriate number of significant figures? As you do calculations, it really depends on the data that you are given. Okay, so this pH will be rounded down in this case to 12, and I just write down 2 significant figure like that. In the next part of the question, for part B, I have HClO. The fact that they give me a Ka means weak acid because it's in equilibrium. So what I have then is, I can imagine that if it is a weak acid, it dissociates partially in solution into H plus ion because it's a weak acid. So I can imagine that Ka equal to H plus ClO minus and then HClO. Alright, of course this can then be approximated to H plus square over the HClO initial, because it's a weak acid, very little of it dissociates into H plus and ClO minus, so the concentration equilibrium is roughly the same as the concentration initially. So what could I do with all this information? They want me to calculate pH, and pH is related to the H plus concentration. So what I do is I have these, I can make H plus my subject. So H plus is going to be square root of Ka times HClO initial. So if you sub all that into your calculator, I think I'll just move this down to a new page so that I'll not be running out of space or something like that. Okay, so I have all the space I need here. So it's really up to you if you want to rearrange it like that, or you can just put in your equation straight away. But I always find it easier if I see what I am doing, then it's less likely that I will make a mistake. So you want to do the inside first before you actually square root the whole thing. So actually, I'm not going to calculate an exact value. You can calculate the exact value yourself. But pH equal to minus log 10 of H+. So with that previous answer on my calculator, I can just press on my calculator and I'll get 4.7147. And I'll run this up to 3 significant figure because the data given in the question was the 3 significant figure, although this was the 2 sig fig. So I think anywhere between 2 to 3 sig fig will have been appropriate given the data for this particular question, right? So if I just run it up to 3 significant figure, it will be 4.71 based on the data appropriation. That would be considered all right. I think I'll just use a new page for the next bit of the question. So this is question 4, C part 1. This is to do with partition coefficient. So partition coefficient is one of those things in A2. They are not very popular, but when it comes out because it is in the syllabus. So you can't say the examiner lied to you because they never lied to you. They just say that you have to know everything that you're supposed to know. Okay, so they say the partition coefficient KPC for ethanamide. Ethanamide is an amide in water and also octane 1-ol. So the reason of me writing this down is because there's something about the information given. They mention this one first. This one is mentioned first. Since they mention this one first, the concentration of ethanamide in water will appear on top of your KPC expression, whereas this is ethanamide in alcohol will appear at the bottom because it's mentioned the second time. So essentially what I'm saying is your KPC expression is going to be the concentration of the ethanamide in water, there you go, like that, divided by the concentration of the ethanamide in alcohol, there you go, just like that. All right, so we have our expression, but we really must be thinking about our equilibrium, what is actually happening in our equilibrium. Okay, so if I have in water, do I want that in water? Nope, I want that on the right hand side, and this one is in alcohol. Okay, so initially, what is my initial mass? Let me see. Okay, so my initial mass, initially I have 1.00 gram there, and then I added to 50.0 cm3 of water. So volume of water is 50.0 cm3. Volume of alcohol is is it 50? Yeah, it's also 50.0 cm3. But it is the mass at equilibrium that is very, very important. The mass at equilibrium is going to tell you the concentration of the ethanamide at equilibrium. For that 1 mark, it's a really straightforward question. So in water, the water layer, they say the water layer, the very last bit of the sentence before the start of question 1, the water layer, the aqueous layer, contains 0.935 gram. So if you have 0.935 gram, initially you have 1 gram, but then after you shake it with alcohol, after you put in some alcohol and then you shake it, you no longer have 1 gram because some of it has gone into the alcohol. So the difference between the masses is whatever that has gone into the alcohol, and that's going to be 0.065 gram. This is to do with solubility. Solubility can be interpreted as a concentration, whether it's in mole per dm cube, or in the case of KPC, is usually what we talk about in terms of mass per volume. So the KPC, since we have the water mentioned first, ethanamide in water, and then the alcohol, so this thing appear on top. So I need the concentration, so 0.935 gram divided by 50.0 cm3. There's no need for me to convert any unit because the unit will very nicely cancel out if I'm very careful of what I'm doing. Ethanamide in alcohol, this is the mass, this is the volume. So there is the gram divided by 50.0 cm3. So as you can see, the gram and the gram cancel, the cm3 and the cm3 cancel. KPC does not have any unit whatsoever. And I'll get this to 14.4, and this is to 3 significant figure. As you could see, what is justified in the data given, 1, 2, and 3, 1, 2, and 3. This is 2 significant figure, this 1, 2, and 3. So I could say between 2 and 3 will be alright, but since 3 out of the 4 data is to 3 significant figure, I would say 3 sig fig is more appropriate rather than 2 sig fig. Okay. Not too sure if I have enough space here, but let me try and complete the rest of the question. So this is question 4, C part 2. So what do we know now? So they say that the portion from the last part of the question, so this is the water layer, and then you shaken with another 100.0 cm³ of ethanol. Sorry, not ethanol, octane 1-ol. So you try to extract, you try to get more out into the alcohol by using more alcohol, and the volume is different now. So if I have the exact same thing, let me just copy paste the whole thing. Of course, in the real thing, you might have to write them down. There's the beauty of knowing all this already, then it's a lot easier for you to write them down, okay? So my initial mass will no longer be 1 gram because I've already extracted some of it into the alcohol originally. So now the 50.0 cm³, now you have 50.0 cm³, you only have 0.935 gram of ethanamide left in the water layer, the aqueous layer. Now you have 100 cm³ of alcohol, and you want to know how much mass there's dissolved in it at equilibrium. So you have 0 there because you haven't added the alcohol. Now you add the alcohol. So let's say this is what you want. You know X gram goes into the alcohol. X gram has gone from here into the alcohol. So how much is left over? You get 0.935 minus X gram. But we know that under the same conditions, so they say under the same conditions, this experiment was repeated, but with a larger volume of alcohol. So the KPC is going to be constant as per the value calculated from the previous part of the question. I got 14.4, but actually I got 14.385, quite exact in the last part of the question. So my KPC, which was actually 14.385. Okay, so if I said that, so that will be equal to the mass of the ethanamide over the volume in water. So it's 0.935 minus X over 50.0, and then the whole thing divided by the solubility, meaning the mass concentration of the ethanamide in alcohol, so X over 100.0. So essentially this is an exercise of rearranging the formula and also finding X. Okay, so let's try that. So 14.385X over 100 equal to 0.935 minus X over 50. Of course, if you bring up the 50 and you bring out the 100, I hope you can see that there's 100 times 0.935 minus X, and you get 14.385X multiplied by 50. Don't forget in an expansion involving bracket like this, so you gotta multiply 100 by this and 100 by that. Then there's my whole point of actually doing it step by step. Otherwise you could have done it, you know, like whichever way you like it. If you can do the shortcut, you do the shortcut. So 14.385 multiplied by 50, I get 719.25X, and then 100 times 0.935, I get 93.5, and then I get 100X. So X is going to be something divided by 819.25. Because you can move the plus 100 to the other side, you get 719.25 plus 100, you get 819.25X equal to 93.5. And then you make X the subject by moving the 819.25 down there, and you will get 93.5 divided by 819.25. So I've gotten my answer as X equal to 0.114. Suppose if I do one more significant figure, and then I can just say I round that up to 0.114 gram. This is the 3 significant figure, and this is the mass of ethanamide that was extracted or dissolved into the alcohol as I mix whatever amount it was in that volume of water, and then I put in some alcohol. I could get this much mass out from that bit into the alcohol as a result of the KPC being constant as long as temperature doesn't change. And I'm rounding my final answer to 3 sig fig, well, simply because one or two of the data. So this is 50.0, this is 3 sig fig, this is actually 4 significant figure, this is 3 sig fig, so 3 to 4 significant figure I think would have been appropriate given the data in that particular question. So that's the end of that 7-mark question on KPC. Next question, so this is a question 5. Question 5 started out on case step. So K step is another equilibrium constant. If you write the equation, you should know that copper 2 plus aqueous refer to this copper hexa-aqua complex. This is a pale blue solution. You should have done this as part of your copper 2 case study chemistry, whether you were in O-level or IGCSE, or even now you're in an A-level, you should have at least seen this at least once, okay? So when I add in ammonia, I'll get this dark blue complex, which is actually incomplete substitution. Incomplete substitution because not only you have 4 ammonia, you actually have 2 water as well. This is supposed to be the resulting complex, still retaining the +2 charge. This is the dark blue complex, the dark blue solution that you get in excess ammonia. Okay, if you haven't seen this before, I suggest you browse through my experimental tutorial playlist. You can see chemistry of copper 2, where I actually demonstrated these color changes. It's very interesting to actually learn transition metals in terms of actual practical, because you remember better as you do it yourself, but probably because of COVID or other cases, you might not be able to do the practical. At least having seen the practical itself, having seen the color changes, it makes more sense to you in terms of remembering or learning the particular case studies on the chemistry of copper 2 as well as chemistry of cobalt 2 in another separate experimental tutorial video. Of course, the complex that is shown in this particular question, they don't show the one with the water, but by right, it's actually still an octahedral complex. It's an incomplete substitution of all the 6 water ligand. So you still have 2 water ligand, but just in line with the question, we'll just use the one without the water, just with the 4 ammonia. It actually still retains the 2 water molecule in the octahedral coordination. So what we have here then is 4 water molecule, and therefore if we are doing as per the example given in this particular question, then we'll kick out 6 water, which we know is not true based on what I just told you. It's actually 4 water that gets kicked out because you still have 2 water ligand left on the copper 2 plus, which is not shown here. However, when you have K step, you ignore the concentration of H2O, so that you only focus on the concentration of the complex and the resulting ligand that are not water. So you're not required to write this equation, but I thought it would be quite nice to actually see from the equation that is called concentration of the substance on the right hand side. So this first square bracket refer to the formula of the complex, the copper 2 plus, the charge is outside. This is not power, this is the charge of the complex. K step is to do with concentration, so another big square bracket. This is one of those mistakes that some students make. They just forget that there's a square bracket to represent concentration, and this is not concentration, this is the formula for the complex, because this is not the power to which you rest the concentration, this is simply the charge of the resulting complex. So that thing has to be divided by the copper H2O 6. So again, this is the formula of the complex, and then I put a big square bracket to represent the concentration of that particular complex. And then I have ammonia, but I have 4 because the stoichiometry equation show me 4 there, so I need to the power of 4. The question doesn't ask you to do this, but in certain years, they do ask you to work out the concentration, the unit of the K step, sorry. So as per the expression, I will have mole per dm cubed like that. And then this and this will cancel out because this and this will have the same unit. So it's 1 over that, which means you got to express it into the simplest form. It's mole minus 4 dm plus 12. When they do ask you, this is worth another mark, but they only want this one, so this is your 1 mark. You do not have to do whatever the question doesn't ask you to do. And they do ask you for the color of this copper with 4 ammonia. This complex is dark blue. It's part of your case study. In the syllabus, it says candidates should be able to appreciate or understand or state all those color changes, write equations when you have water, ammonia, OH minus as well as chloride ligands surrounding copper 2 plus as well as cobalt 2 plus. Have a look through the A2 transition metal syllabus. Moving on to the next part of the question, so part B, there's a lot of information given here. They are saying that when you heat this thing, so remember this thing is in aqueous solution, so when you heat it, you can give off ammonia, not too surprisingly, okay? And then some of the NH3 remains in solution and some forms NH3. But then the color changes from this dark blue solution.
And then what you get is you also get copper OH twice. This is a precipitate. This is a pale blue precipitate because the NH3 in small amounts can act as a base. So just like any sodium hydroxide added to anything that contains copper 2 plus, it will precipitate out the copper 2 hydroxide because it's a classic precipitation reaction from IGCSE or O-level chemistry. So this NH3 in a small amount because some of the NH3 will escape as a gas as you apply heat to it. Alright, so this is a pale blue precipitate that get collected, and then once you add this pale blue precipitate, so this is a pale blue precipitate. If I just NH3 in small amounts is a base, is a weak base. What happened with this precipitate is you add in some concentrated HCl, then you will get a green complex. They don't tell you it's green, but this is actually green complex. It's CuCl4 2 minus because each of the copper is copper 2 plus and each of the chloride is a minus 1 ligand. So one of the plus 2 and then minus 1, minus 1, minus 1, minus 1, altogether minus 4. You get a 2 minus complex. This is part of your case study. And then a sample of copper 2 hydroxide is added to dilute sulfuric acid. When you add to dilute sulfuric acid, this is an acid, this is a hydroxide, this is a hydroxide. Hydroxide is a base, is an alkali, so you are going to get an acid-base neutralization reaction. So acid-base neutralization, this is your year 9 type of reaction concept. So you will get a salt, which is copper to sulfate, and you get water. Of course, there's no balance equation here that is left up to you to do. Okay, so this reaction forms a colored copper complex. This is not the complex. You are in water. You are in solution. So what actually happened is this thing is in solution. In solution means you will not just get copper to sulfate crystallizing out. Instead, what you will get is you will get back the copper H2O6 2 plus complex. So this is going to be Z, whereas the other one just now, copper tetrachloride, CuCl4 2 minus, this was Y, and this was the dark blue solution that you started with. This is the product you get when you have copper 2 plus aqueous solution. When you add this in excess ammonia, you're going to get this particular result. And that was the first part, the very part A of this particular question. Okay. So moving on to this question, what is the essence of this thing they want you to do? They say suggest an equation for the reaction of this thing to form this as you are heating it. Okay, so this is a very, very tricky one because you are forming this. So you are forming this, then we got to get rid of the ammonia. But how do we get rid of some as ammonia? But some of them remain in solution. The one that remain in solution is going to give you a weak base. So that means some of them will become NH4 plus as well as OH minus. The OH minus is being taken up by the copper 2 plus to form copper 2 hydroxide, which means you're going to end up with a little bit of ammonium ion. Alright? So our equation for part B, our equation is going to be copper with 4 NH3, supposedly with 2 water as well, but doesn't matter. You're going to add that with, well, what happened is you gotta heat it. I say you gotta add it with something because I already balanced this equation and it doesn't make sense without adding something to it. But let's see what are the product. You will get copper hydroxide. Can you see that you end up with copper 2 hydroxide, which is the pale blue precipitate, but there's no oxygen there. So you got to add something there to give you that thing. Without the oxygen, you are not going to be able to form something with oxygen because you're doing chemistry and you're not doing nuclear physics. All right. You do release ammonia gas. That's what they told you. But some of the ammonia remain in solution if you read the question earlier. And they remain in solution and they act as a weak base. When they act as a weak base, they give you hydroxide ion as well as ammonium ion. The hydroxide ion reacts with copper 2 plus and precipitate out this copper 2 hydroxide, leaving you NH4 plus. And it makes sense to have no charge, and this thing has to be charged species because it started with charged species plus no charge. Alright, there's 2 hydroxide, so I will have 2 water molecule. And it's because of the 2 ammonia forming you 2 NH4 plus. That's why you get 2 OH minus that form the copper 2 hydroxide, therefore leaving you 2 ammonia that is formed as a gas. So this equation is balanced just like that. Next up, this is still question, I think this is question 5 already, isn't it? Yep, this is question 5. So it's also another balancing equation. So they want you to suggest an equation from the copper 2 hydroxide plus the hydrochloric acid. So remember, this was the pale blue precipitate that you know from your O-level, IGCSE. This is corn HCl. Then you're going to get the green complex. You can see this, how green it is from my experimental tutorial playlist. So what happened then, it will kick out the OH minus, but don't forget H plus and OH minus will do neutralization. So you have 2 OH minus to be kicked out, so you will form 2 H2O. And of course, you're in acidic condition, so since you have 4 chlorine, you must have 4 HCl, but you only need 2 of the H plus. You only need 2 of the H plus out of the 4 H plus to neutralize the 2 OH minus. So you only form 2 water, and therefore you're left with 2 H plus. And your equation, no charge, so no charge on the left. This is 2 minus because it's copper 2 plus, and then minus 1 times 4 because you have 4 chloride ligand. Overall, you have 2 minus charge, and that's why you must have something, the H plus there. Plus 1 times 2 is plus 2, cancel out the charge because this is no charge. Equation that you write starting from O-level or IGCSE has to be balanced every time you write equation. Okay, so part D is about this case study. So they're asking for what happened to Y, what happened to Z. They're asking for the color. So the color of the complex, as I said earlier, so this complex is CuCl4 2 minus, and as I talked about earlier, that Z is actually this copper 2 sulfate salt dissolved in water, because the last step is copper 2 hydroxide, which is a base reacting with acid to get salt and water because it's neutralization. This in water is not this, so the complex is not this. The complex is actually this thing, the copper with 6 water around it, so it's a pale blue solution. That's why they say it's a colored solution. So Z is going to be your copper with 6 water. We call it copper hexaaqua complex, if I move that down a little bit. So this first thing, Y is a green complex, whereas Z is a pale blue solution, is a pale blue complex. In terms of geometry, so this one has got 4 monodentate ligand. It's actually tetrahedral complex. Chloride is much bigger than hydroxide or water, and therefore you can only fit 4 of them around metal center. Whereas for the water, which are smaller in size compared to the chloride, you can fit 6 of these monodentate ligand. Coordination number 6 is going to be octahedral complex, and they're asking for the formula, so I will just write down the formula down there. They have already bolded this thing, so they are not asking for the formula of this, but if they do ask for the formula, it's going to be this thing. 1 of the copper is plus 2, 4 of the Cl minus, that means plus 2 minus 4 give you 2 minus. Alright. Part E, so question 5, part E is this fixed essay kind of question, and there's actually the last bit of this transition metal, 12-mark question, is 5 marks, alright? So they're asking for why. Why are the complexes colored? This kind of essay is very common, and you should be prepared for this kind of essay as you are preparing for paper 4, amongst many other essays such as thermal stability of group 2 carbonates or group 2 nitrates, as well as solubility of group 2 hydroxides or group 2 sulfate. You just never know when this kind of essay is going to come out, but if they come out, they are mostly things that you can prepare. Remember that we talk about degenerate d orbitals. So these are called degenerate d orbitals because they are of the same energy. So these are degenerate d orbitals. They have the same energy. Alright, so what happened? I think I will run out of space there. So what I'll do is I will just probably best to just do it on a new page so that I don't have to worry about running out of space or something. In the presence of ligand, what this one would do is, in the presence of ligands, so this is just M, this is, let's say Ml6, so this is octahedral complex. You're going to destabilize some of them, they're going to split, When they split, they're going to split in this order. They will get destabilized, meaning they rise up in energy compared to the degenerate d orbital's original energy. And then you will have three sets here. So the lower energy set comprises of the dxy, dyz as well as dxz combination, whereas the one of the higher energy levels is going to be the dx square y square and dz square combination, because the electrons in these orbitals, they repel more with the ligands that come in along the axis, and therefore they repel more with the electrons here, destabilizing it a bit more. What is important is, just now you had the same energy, now there is a separation between the lower energy level and the higher energy level. The definition of transition metal, they are not asking for this diagram here, but in certain years they do ask for this diagram. I thought it'd be best if I actually explain it in terms of this diagram before I actually move on. Okay, so the definition of transition metals is stated in your syllabus. So an element that form ions that have incompletely filled d subshell. Incompletely filled d subshell. And if you have incompletely filled d subshell, that means you are bound to have at least one electrons in the lower energy levels, and that means that electron from the lower energy levels can get promoted or excited to go up to the higher energy levels, and they can only do this if they absorb energy that correspond to this energy gap. So delta E equal to Planck constant times the frequency of the radiation, and this happen to be visible light radiation, so they are electromagnetic wave, which means either you know this formula or you just gotta remember that delta E is inversely proportional to the lambda, meaning the wavelength of the visible light being absorbed. Okay, in terms of the physics, don't worry too much about it, but in terms of the explanation, the fixed essay, okay, so in the presence of ligand, the degenerate set of d orbitals, so those 5 lines refer to the d orbitals. They become non-degenerate. They split into 2 sets. The lower energy set, consists of dxy, dyz, and dxz. The higher energy set, these are probably not required actually, but anyway, it consists of dx square y square and dz square. Okay, so this part is probably not required as part of the essay, but I just thought it'd be interesting because I think I've seen questions where they ask you draw an orbital from the lower energy level, draw an orbital from the higher energy level. Of course, if you don't know what you're talking about, then how can you do that, right? Anyway, moving on to the next bit of the point. So the electron in the lower energy level, remember that we define transition metals having incompletely filled d subshell, so you always have at least one electron in the lower energy level. They can get excited or they can get promoted, whichever word you like, excited or promoted to the higher energy level. And how do they do that? They have to absorb by absorbing photons. So photons refer to light particles in the visible light region. Visible light region refers to RGB, the colors of the rainbow. So the energy gap, so we already talked about that there is a separation of the 2 sets of the d orbitals, the 2 sets of them. So the energy gap, delta E, is equal to Planck constant. You don't need to know about the Planck constant, I guess, if you don't do physics, but it's just a constant. And this is the frequency of the radiation. And this is equal to hc over lambda, where it's Planck constant times the speed of light, divided by the wavelength of the visible light being absorbed. So lambda is equal to wavelength of visible light absorbed. So why is this important? Because out of RGB, whatever color that is being absorbed is not what you see. The color you see, the color observed, the color of complexes observed is complementary to that is being absorbed. Is complementary to the color absorbed, because you do not see the color that's being absorbed. You see the color that are not being absorbed, meaning you see the color that's complementary to the colors that will absorb. As the electrons in the lower energy levels, they get excited, they absorb certain colors, so the colors that will not absorb, they will pass through. Okay, so that's it really for the 4 marks out of the 5 mark essay. But I said 4 out of 5 marks because there's another question that we haven't answered. So this energy gap can change as ligands change. So ligand change, as the metal change, then this energy gap will change. As the oxidation state changes, even though you are the same metal but you have different oxidation state, like iron 2 plus versus iron 3 plus, this energy gap can change as well. So there are 3 factors. So 3 factors affecting delta E. First of all is the ligand, obviously. Different ligand, different delta E, different lambda absorb, different color. Okay. Second one is oxidation state of the metal. Different oxidation state of the metal, like iron 2 plus versus iron 3 plus, cobalt 2 plus versus cobalt 3 plus, etc. etc. Different delta E, different lambda absorb, different colors. Okay. And last but not least is the M itself. All right. So the metal itself, different metal, different splitting, different lambda absorb, different colors that you will absorb, and therefore different colors of the complexes that you will see. So this thing, the factors itself, would refer to or will result in different colors for the complexes, and that is the essence of the last bit of that essay. If I just squeeze this down a little bit so I can move up my whole thing, so I can just put in the last bit of the explanation down there. So if I just use a different color to complete the essay, so Y and Z just now, remember their formula. So they have different ligands. They have different ligands on the metals. Perhaps I could mention what ligands it was. Cl minus versus H2O, Cl minus for Y, H2O for Z. Different geometry as well, by the way, and also different geometry. Different shape. One was tetrahedral, one was octahedral. So therefore, I can say different delta E. This is the energy gap, which I already defined earlier. Different lambda absorb, which again I also defined earlier. So different lambda absorb means you will see different complementary colors. All right, I hope that makes sense there. So that's the end of that 12 mark traditional metal questions. So the next question 6, is again about transition metals. So it seems like they might as well just continue the previous question, but anyway, they didn't want to, so because they're asking you on something different, I guess. They started out by asking you to define monodentate ligands. So there's always a lot of marks on definitions. You gotta talk about dative covalent bond, and since it's monodentate, you gotta talk about one lone pair, at least one lone pair, and therefore one dative bond per ligand molecules. So monodentate ligand has at least one lone pair. All right. So I'm not saying that it must have one lone pair, but it has at least one lone pair. Okay, it can have more than one lone pair, but that's what it uses. Okay, one lone pair that forms one dative covalent bond to metal ion center per ligand molecule. This is very, very important. Per ligand molecule, or per ligand, or just per ligand, I guess, because ligand can be molecule, ligand can be ion. But what is very important is the idea of dative covalent bond. And when they form dative covalent bond, they will form a complex that forms one dative covalent bond per ligand, producing a complex, I guess, forming a complex, producing a metal complex. So once you have ligand forming dative bond onto metal center, you can get a metal complex. Importantly, monodentate means they just form one dative bond per ligand. A lot of students will miss out the idea of per ligand, because then when you have bidentate ligand, then you will have formed two dative covalent bonds per ligand molecule or per ligand ion, and they all form complexes. Okay, So the next part of the question is basically about this S2O3 2 minus. S2O3 2 minus, they tell you that it's monodentate, and then they are telling you that Ag plus is linear. Linear meaning, well, 2 bond pair and 0 lone pair. In the context of inorganic chemistry or complexes, we are thinking about two times dative bond. 2 times dative bond. So we have monodentate ligand. 2 times dative bond means 2 times monodentate ligand. So we will be thinking about Ag plus as well as S2O3 2 minus and S2O3 2 minus. How are you going to combine them? You're going to get Ag, S2O3. This is a plus 1, and then you get a plus minus 2, plus minus 2. There's going to be your overall charge. Plus 1 minus 4 is going to give you minus 3. So we use a big square bracket to represent the charge on the complex. So Ag, S2O3 3 minus, including the charge. So there's just 1 mark for that particular complex there. I think I made a mistake there. There should be 2 of the S2O3 2 minus, as I did show 2 of them, and I did account for the charge, so it should be Ag S2O3, 2 of them. Alright. So moving on to the next part of the question. So you have part B. You have a second linear complex. They say with NaCN, if you remember what you have done from AS organic, is to do with NaCN as a catalyst for the nucleophilic addition of HCN onto ketones or aldehydes. So this is a monodentate ligand because you have a lone pair on the carbon. So being a monodentate ligand, it can replace the S2O3 2 minus, and that's exactly what this question is asking you to do. So from the previous complex P, we started from the one with 2 of the S2O3 2 minus ligand. Oops, sorry, it's not 2 minus, it's 3 minus. In fact, it's written as 3 minus previously. And then you react with NaCN, and they say that you get a linear complex, a second linear complex. So Cn twice, and this is Ag plus 1, and then this is a minus 1 ligand. So you have 2 of them. So plus 1, minus 1, minus 1. You're going to end up with overall minus 1. I think it's best if I move my equation down there because, yeah, so that I will not run out of space. And what happened is I'll kick out my S2O3 2 minus. But don't forget that I started with NaCN, so I should have Na plus as my spectator ion lingering around here. If you have Na plus and you have S2O3 2 minus, you can hopefully imagine that the charges have to cancel out in order to give you the compound in terms of how to get the formula of the ion. I hope you remember that the cross multiply method is basically a lowest common multiple from primary school mathematics. Then the LCM of 1 and 2 is 2. So that's why you need 2 of the Na plus and 1 of the S2O3 2 minus. So you need 2 of the Na plus and 1 of the S2O3 2 minus. Okay, and because you are kicking out 2 of the. Does that make sense at all? Let me think. Why does that look so weird? That looks a bit weird. Okay, never mind. So I do have 2 Cn minus, so I need 2 NaCN, and I have 2 sodium, so I have 2 sodium. I have 2 thiosulfate or 2 S2O3 2 minus, but I only have 1 S2O3 there. I cannot create another one out of nowhere. So what I can do is I must kick out another S2O3 2 minus on the right hand side. So plus S2O3 2 minus. Because then you can see minus 3 and no charge give you minus 3 on the left. This is minus 1. This is a compound with no charge. There's what you had done ever since you were in O-level or IGCSE level chemistry. The idea is to get a compound with no charge. Minus 1, no charge, minus 2 ion, overall minus 3. The charges balance, the atom balance, write an equation only for 1 mark. You cannot afford to lose it if you don't know how to balance equation at all. So that was B part 1. And now moving on to B part 2, they say suggest a reason. So this is complex P, this is complex Q, this one is Q. This is the second linear complex. And they say why the concentration of Q is much greater than the concentration of P in that mixture. Well, the fact that you're forming these and all of this will be in equilibrium because the part 3 is to do with ligand substitution. So the type of reaction is ligand substitution. So I've kind of moved on to part 3 because you are doing a ligand substituting or replacing this particular ligand, and you form another complex and you kick out that ligand. So you're replacing one ligand with another ligand. That's why in part 3 this is about ligand substitution reaction. Going back to this reaction, all of these are actually in equilibrium. The fact that you have more of these or these in higher concentration than these is a result of you forming a more stable complex. So Q must be a more stable complex. So Q is a more stable complex than P. Okay, or K step for Q, stability constant for Q must be higher than stability constant for P. Higher than K step of P. Alright, so K step was one of the earlier questions to do with stability constant in question number 5, the previous question. So you can look through the idea of K step if you're unfamiliar with that. Now the next part of the question, it was already what I mentioned. This is very clearly a ligand substitution reaction. You are replacing the S2O3 2- with a Cn- ligand, in fact with two of them. So you still have the linear geometry, but the charges have changed because S2O3 was a 2- ligand, whereas Cn is a Cn- ligand. Moving to the next part of the question. So part C is to do with platinum complex. So what you have is you have platinum and then Cn twice and Cl2 twice. This one, the platinum is unknown, oxidation number. So let's say we have platinum unknown, and then we have 2 of the Cn-, each of which is -1 charge, therefore -1 oxidation state. And then you have 2 of the chloride as a ligand. So chloride as a ligand is -1 oxidation state. Overall oxidation state of the ion, the complex ion, is -2. This gives us platinum -2, +2, and then +2 again. So this is going to be platinum +2 oxidation state. They're telling us that there are only 2 isomers. Only 2 isomers of this complex, and they say is stereoisomerism. Stereoisomerism. So platinum +2 complex is a D8 square planar complex, and this is in line with the idea of stereoisomerism there, not because it has a chiral center. In fact, it does not have a chiral center because what you have actually is you do not have 4 groups of atoms that are different, so you cannot be talking about optical isomer. Instead, you're talking about geometric isomer, which are the cis and the trans isomers. So draw the structures of these 2 isomers. For that 1 mark, you are just drawing in 3-dimensional. So I'm drawing this as a sideway structure where these 2 are coming out towards you from the screen, from the paper, and these 2 are moving away from you behind the screen, okay? So the chloride and the chloride 180 degree to each other, the Cn and the Cn 180 degree to each other. Whenever you draw complex, always try to draw the ion, the full ion of the complex itself, okay? So what I'll do is I'll just copy paste this so that I don't have to redo it again. But this time I will just swap the Cl and the Cn so that the Cl and the Cl and the Cn and the Cn are 90 degree apart. This might look bigger than this, but in reality, in a square planar complex, this is a square plant. I could have drawn, you would have been right if you have drawn these because they are exactly the same. It's just that this one is showing it flat in the surface of the, in the paper or in the screen itself. This is flat, but I'm just tilting it 90 degrees so that these 2 are pointing out and these 2 are pointing away from you. But it's totally flat. It's actually 90 degree, 90 degree, 90 degree, and 90 degree. That's the idea of a square planar complex. All right. So even if you draw these and drawn similarly like that for the other one, you will have gotten the mark as well. Okay. So describe the geometry. Oh, I already done that. So the geometry is just square planar. And name the type of isomerism. I have already done that as well. This is called geometric isomerism. This is geometric isomerism in transition metal complexes, which is to do with cis and trans. So the Cl and the Cl, the Cn and the Cn are on opposite side. This is what you call the trans isomer, and this is the cis isomer. So that's the end of that 9-mark question there.
Moving on to the next question. So question 7 is to do with organic chemistry. So you have phenol. So phenol is a weak acid. So phenol is this benzene ring bonded to OH, and it's a weak acid. So when you dissociate in water, you're going to dissociate partially or ionizes partially, or the idea is reversibly into H plus, which in the presence of water is going to be picked up by H2O, and therefore you get H3O plus. H plus in water is going to be H3O plus. Okay, so phenol can be made from phenylamine. Phenylamine is a benzene ring bonded to a NH2. This is called a phenylamine. So how do you make phenylamine to phenol? Well, there are multi-step to it, but the idea really is the key step in between is going to be this diazonium. The diazonium is very, very important chemistry, something you have got to know as part of your case study. It's a diazonium chloride. Basically, the nitrogen forms 4 covalent bond there, but it's a linear geometry because it has got 2 bond pair. So this is 1 sigma, this is 1 sigma and 2 pi, but altogether you got 2 bond pair and 0 lone pair around the central nitrogen. This is to do with shape of molecules, so it's 180 degree there. And the nitrogen only form 4 covalent bonds because nitrogen is a second period element. So 2s and 2p, maximum only 8 electrons in the outer shell. It cannot form 5 bonds. So students who draw a covalent bond to chlorine is actually wrong. This is actually ionic. Okay. So what happened then is the N2 wants to leave as a gas, and therefore you can put in a nucleophile such as OH minus or H2O. Typically we are just adding H2O and let it warm up to room temperature because this one needs to be kept cold. This is the diazotization, so basically forming the diazonium chloride. This is called diazonium. RNN or Rn2 plus Cl minus is called diazonium chloride. Anyway, so they're not asking for much for that 2 marks. They're asking for reagents. So your reagents for your first step is going to be dilute HCl as well as NaNO2. This is called sodium nitrite. NO2 minus is called nitrite. Nitrite is actually an O-level or IGCSE syllabus under qualitative analysis, and you also have NO2 minus nitrite as part of your paper 3 qualitative analysis in your AS paper 3, which means they could ask you in theory anytime they want to. This is called sodium nitrite. Make sure you don't get confused. All right, so we're gonna do this at cold temperature, so around 0 degrees Celsius. The second step of which is going from here to here. I'm just adding water. So just add water, liquid water essentially, and then warm to room temperature. You just let it warm up to room temperature, which is 25 degrees Celsius slowly, and then the N2 will escape as a gas. The N2 will escape as a gas, and the water will go in and sub out the vacancy, and then it will form HCl as a result because you still have Cl minus, but then you have removing the H from the H2O itself. Okay, so the next bit of the question, so 7b, it says phenol reacts with dilute aqueous nitric acid. So this is going to be the nitration of phenol. As you know, phenol is very reactive to electrophilic substitution. You can do it at room temperature. No need reflux. You don't even need concentrated nitric acid. You can do it with dilute, and you also don't need reflux because very rich benzene ring, and it's all down to the OH bonded to the benzene ring. Okay, so we know that from the data booklet. You can see that the OH is 246 directing. We call this ortho and para directing, depending on which teacher actually teaches you or which textbook you refer to. The data booklet don't refer to ortho or para, but ortho is basically the 2 and the 6 position. The para is the 4 position, but doesn't matter. 2, 4, 6 directing mean ortho and para directing. And they want you to draw the structural formula and name each product. So we know it's a nitration. So if you have OH there, this is going to be your position 1, and this is 2, 3, 4, 5, 6.
Of course, you could also say if this is position 1, then this is 2, 3, 4, 5, 6. It doesn't matter. They are exactly identical. So what happened then is one of your first product, single nitration, is going to be OH there, and then NO2 at position 2. All right. So based on the molecular formula given is C6H5NO3. So what does this tell you? This tells you single nitration. So you don't get double nitration product. This information tells you single nitration, and that product is going to be, how do you name it? This is a phenol. This is a NO2 at position 2. This is called 2-nitrophenol. The nitro group is at position 2, is a phenol, so 2-nitrophenol. Of course, then I could draw the other isomer, where it will be directed at position 4, not at 3, because from the data booklet 246 directing. So I'll get 4-nitrophenol. 4-nitrophenol. And those two are the ones that are required by this particular question. They want you to draw, they want you to name that particular compound, those particular isomers, really. So question 7, part C, what do we have? Phenol reacts with excess of aqueous bromine. So again, this is aqueous bromine, and this is going to be electrophilic. Substitution on the benzene ring. And this is a result of the very rich benzene ring due to the OH bonded to the benzene. They want you to draw N-name. So we know that this reaction actually produces a white precipitate because this is aqueous bromine, and the phenol itself, even though it's soluble in water, but this resulting product where it's directed to 2, 4, and 6 position. So it's a tribromophenol. In fact, it's a 2 because it's 1 and it's 2, 4, 2, 3, 4, 5, 6. So it's 2, 4, 6 tribromophenol. 2,4,6 tribromophenol is insoluble in water, and as a result of its insolubility in water, and you're in aqueous bromine, it will actually crash out as a white precipitate. All right, so they don't actually ask you to write the equation here, okay, but sometimes, so this is extra bit, sometimes they do actually ask you to write the equation, so make sure you know you can write the equation on what is going on. So when you add bromine, you're going to get that thing. It's a lot easier from this kind of diagram because you can see what is going on. It's an electrophilic substitution. So you kick out a H, and a H. So you kick out 3H. But then you don't use all the Br. You actually only use the electrophile. So you only use the Br plus, which means the Br minus is going to combine with the H plus, and you will kick out 3 Br minus. And that is why you get 3HBr, 3H plus from the position that you're substituting, and then you're adding in Br plus, so you're kicking out Br minus, so you kick out 3 Br minus to combine with 3H plus. This equation must be balanced with 3Br2. Okay, so this is not required by this question. Of course, this is the only one required by the question, but you never know. They might actually ask you in a different kind of scenario, and they have asked you in a different kind of scenario in a different paper form. Okay, so they want you to describe visual observations, because they don't want you to focus on other type of observations. This thing actually smell a bit like Dettol. Dettol is this antiseptic brand. It really smells antiseptic. Okay, so this has the smell of Dettol. If you ever made it before, then you might have smelled Dettol before. So this thing smells quite a lot about the same as Dettol. All right. Anyway, so in terms of observation 1, so if you look at this particular equation, so we know aqueous bromine is kind of orangey yellow. So aqueous bromine is orangey yellow. It reacts just like it reacts with alkene. Therefore, the orange yellow solution, bromine or bromine aqueous solution, aqueous bromine, gets decolorized. So basically, they turn colorless from orange yellow to colorless as they get used up. Okay, in terms of observation 2, we get a white precipitate because the resulting product 2,4,6 tribromophenol is actually insoluble in water. And where does the water come from? The water comes from aqueous bromine. You are adding excess aqueous bromine. All right, so a white precipitate is formed or a white precipitate is produced. Part D, you want a neutralization where a phenol acts as an acid. So this is the structural formula of it, but when you write equations, you don't have much choice except to write C6H5OH plus NaOH. So this is going to be the acid, and this is going to be the base. The acid donates the H plus. The base accepts the H plus. So in a classic year 9 IGCSE or O-level chemistry concept, you will give away the H plus and you will get O minus because you lose a H plus, so you become O minus. You lose the OH minus, the OH minus, accept the H plus, and you will get water. And the Na plus suddenly has no partner, and therefore it will just partner with the resulting phenoxide. This is called phenoxide. This is phenol. This is actually called sodium phenoxide. So the ion itself is called phenoxide ion, and that is your salt, and this is your water, because this is your classic acid-base neutralization reaction. Okay, and then part E. So question 7, part E, is one of those fixed essay questions. So you might have seen this. In fact, this is the last part of these 11-mark questions. So comparing relative acidity. So to find out more about this kind of fixed essay question, you can visit my A-level concept playlist, where I never deleted these videos, and you can find out more about relative acidity as well as relative basicity essay, which they often ask in A-level, and you gotta get used to them. All right, so they have given you this thing from most acidic to least acidic. So I find it a lot easier if I start by explaining the concept first, because it's a lot easier to decide what happens after that, rather than remembering stuff which don't make sense to me at all. All right, so acids donate protons. When acid donates protons, the species you get is called conjugate base. So the more stable is the conjugate base. So you should know about conjugate base from AS chemistry under acid and bases, because for example in this bit, so the acid donates the protons, so the resulting thing that you get after you donate the proton, this is called the conjugate base, and then the conjugate base can of course combine with this thing here and give you the resulting salt. I'll show you in a little bit what I mean. So the more stable the conjugate base, the more acidic is the substance. All right, so if we look at phenol, so we got to look at each and every one of these. So when we have phenol, so they reversibly dissociates because it's a weak acid. Remember, it's a weak acid. So they reversibly dissociate in solution, so to give you that, and then they'll give you H3O plus. And we're looking at how stable this one is. So this is called conjugate base because it's what you get after the acid donates the protons. The species that you get is called conjugate base. So the conjugate base of phenol is this phenoxide ion. And you got to decide how stable it is. If you think about this in 3-dimensional, so we know the benzene ring has a carbon sp2 hybridization like that. So what happened that is the oxygen bearing the lone pairs as well as bearing the negative charge there, it can get delocalized into the ring. Okay, who says that you can't draw or sketch something out even when they are giving you lines? No one says you cannot draw things like this, because drawing is very good for your answer. It makes your answer stronger without having to write a lot of words. Okay, so now I can write a few words, I guess, to explain the thing. So the negative charge on the phenoxide ion, which is the conjugate base, gets delocalized into the benzene ring. And this is good because it helps to spread out the charge instead of putting it just on the oxygen. So delocalize into the benzene ring, therefore stabilize. So the negative charge gets stabilized, the conjugate base gets stabilized, so it's reasonably stable. All right, so how about when we look at between H2O and NaOH, ethanol, which is ETOH. So between HOH and H, what am I trying to say? Well, between water and ethanol. So what we have is H2O. Well, we know H2O go to H plus and OH minus because this is KW expression. And then we also have ethanol, so 2 carbon alcohol. If I say reversible, because all of these would be very weak acid anyway. So what we have then is like this and H plus. It's probably easier if I actually have this shown like this. So it's a lot clearer to see what is going on. Hopefully you can see that. This thing is electron donating, but the hydrogen is not just donating because it doesn't contain any carbon. There's only one electron there. But this is a CH2, CH3, so it's an alkyl electron donating group. Alkyl electron donating group is part of the essay in AS chemistry under electrophilic addition to explain the stability of carbocation. All right, so it's not something new to you at all. And yeah, so we can see alkyl, or you can say ethyl electron donating groups destabilizes the ethoxide ion, which is basically CH3 CH2O minus, compared to HO minus. So this doesn't get destabilized, this get destabilized. So we can see that these conjugate base get destabilized, whereas the other conjugate base just now with the O minus is stabilized. Remember what we said earlier? That's why we set the scene just now. The more stable the conjugate base, the more acidic is the substance. So this is more stabilized compared to HO minus, which doesn't have this delocalization into the ring. So this is the more stable conjugate base compared to water. So this is more acidic than water. This is destabilized because of the alkyl electron donating groups that further introduces electron density into something which already is rich in electron. So it's destabilizing the ethoxide or any sort of alkoxide ion, and therefore it becomes less stable than the hydroxide ion. So this thing is going to be less acidic than water. So water is going to be somewhere in between. So the most acidic is going to be phenol, followed by water, and then followed by ethanol, which is the least acidic because the conjugate base get destabilized, the conjugate base gets stabilized. All of this is relative to water. This is a 3-mark essay. I probably spent quite a bit of time on this, but if you're doing this in an exam, point, and point. So the point really is you draw this and you can see it get stabilized by delocalizing the negative charge into the ring. You draw this and you can see this destabilizes the negative charge because this is alkyl electron donating group compared to the hydroxide that come from the water that doesn't do anything. It's just like a middle reference point compared to the phenol, compared to the ethanol. All right, so that's the end of that 11-mark question. It's just a 3-mark essay questions that you could prepare well in advance. On to the next question. So question 8. Benzene can be obtained from crude oil. So what do they want? Benzene can react with bromine. So the catalyst there is obviously like FeBr3 catalyst or AlCO3 catalyst, that kind of stuff. So they want you to think about when you have benzene ring plus Br2, of course, conditions, so it doesn't react easily, not like phenol in the previous part of the question. So you can get Br, but then you will kick HBr out. So the other product, give the name or formula. So if they give me a choice, I would almost always go for the formula because it's a lot easier. If you go for the name, some students will put down hydrobromic acid and you will be very wrong because this is insoluble in water. This is bromine. This is not aqueous bromine. If you want the name, it is called hydrogen bromide. In fact, you have done hydrogen chloride since year 9 under covalent bonding in under the bonding topic. All right. So when you share electron between something that has 1 valence electrons and 7 valence electron, you form a single covalent bond. So it's a simple molecule. It's a simple covalent molecule with a simple molecular structure or simple molecular structure or simple covalent structure with a very low melting and boiling point. Anyway, they want the name or the formula. I would almost always go for the formula because it's less likely I'll make a mistake like this. If you put down hydrobromic acid, you will have made a huge mistake. This is A part 1. A part 2, they want you to do the mechanism. This is actually part of electrophilic substitution mechanism. Depending on what derivative they give you. So here is just a benzene ring. And of course, they just have a Br plus. How do you get the Br plus in the first place? That's a very important question. You use FeBr3, which is like a Lewis acid catalyst. You might not have heard of Lewis acid. It's alright. Lewis acid is basically an electron pair acceptor. So they accept a pair of electrons. And what happened then is they will just form FeBr4 minus, and they will give you your electrophile. So this is your electrophile, and that is basically what has been given in the question. The Br plus is the electrophile. From the benzene ring attack that, I have always maintained the idea that I've got to show the double bonds so that I can follow what is going on. When I attack that like this, then it got a H and a H. I like to show the one with the double bond rather than the one with the delocalization, because I could follow the bond. I could see this carbon has gone from each of these carbon is sp2 hybridized. This carbon is now sp3 hybridized with 1, 2, 3, and 4 covalent bond and 4 sigma covalent bond. 4 bond pair, 0 lone pair is actually 109 degree carbon sp3 hybridized there. This is still 1, 2, and 3 bond pair and no lone pair because this is a carbocation intermediate. This is a carbocation intermediate. And you will have realized that I have written down this thing called slow because that is the rate determining step. It's the slowest step in the overall reaction because you are breaking the aromaticity. You are destroying what makes the benzene ring stable. And as a result of it, in contrast to the alkene chemistry where the Br minus would just attack there, but it doesn't happen in benzene chemistry because the benzene ring wants to go back to being benzene ring. So this is an intermediate as a result of breaking the stabilization is called aromaticity. So I got to restore the aromaticity, which means I want to reform the double bonds. I want to remove this H. I don't remove this H. I remove the H where I am substituting, the H with the Br. So I'm removing this H there, the one that contains the Br already. So I give it back to the carbon there, and I will reform the double bonds, and then I get an alternating double bond like this, which in reality it's not that true. It's actually the delocalization. So what you will get is you get the delocalization back, and you get Br, and this kick out minus H plus. And it is this minus H plus as well as the Br minus from here that you can regenerate that FeBr4 minus plus the H plus that you kick out. Then you get FeBr3 and you get HBr. Remember the equation earlier on? The other product that you get is HBr. In an overall equation, you don't see the FeBr3 because FeBr3 is a catalyst, it's a condition. A catalyst is not used up in the reaction. It is simply involved in the reaction, but you get back the catalyst in the end because you will lose the Br minus and combine with the H plus, giving you the other product as was requested in the early bit of this question. So this is the main mechanism that you're supposed to master for your A2. Okay. So name this mechanism. So very straightforward. They want the name of the mechanism. So this is just electrophilic substitution. This is not electrophilic addition because this is not our normal alkene chemistry. Substitution. Normal alkene doesn't want to go back to this thing because you don't have aromaticity of the benzene ring, so they will just add onto the double bond. But benzene wants to go back to being aromatic. Aromatic means the benzene ring, the delocalization, all these are stabilization, and it is good and favored. Moving to the next part of the question. So I think this is question 8, right? We're already at question 8, so it's coming towards the end of the paper now. So question 8, part B. So we have benzene. So benzene goes to this thing, which is CH2CH3. So we have done, what we have done here is we can chop this, and we can imagine that we have done CH2 CH3 plus. So this is called alkyl group. This is alkylation. This thing is actually Friedel-Crafts alkylation. Is a name reaction as stated in the syllabus. Friedel-Crafts alkylation under the benzene topic. All right. So doesn't happen on its own, obviously. So you need to do some stuff with it. And then after you do KMnO4, and very strangely, so it's KMnO4 and alkaline, but doesn't matter. If they do it in alkaline conditions, it will chop off it will fragment all the alkyl groups, and you will just get CO2H. However, you are in alkaline. If you are in alkaline environment, you will not get carboxylic acid, you will get a salt. So they don't tell you what is the cation, so I'm not going to put down Na plus because I don't know what is the cation on the base itself. All right, so that is the salt, because you're in alkaline condition. Then what happened in step 3 is you get back this thing, CH2OH. So I've just drawn the skeletal. This is CH2OH because carbon form 4 covalent bonds. I only show 1 to carbon, 1 to oxygen, so there's 2 hydrogen there. So this must be reduction because I have gone from a carboxylic acid or carboxylate into the CH2OH. Reduction require reducing agent, and the only one strong enough to reduce carboxylic acid, which of course is not real carboxylic acid because it's carboxylate there. I need AlIAlH4. This is called lithium aluminium hydride, and I need to use it in dry ether because it is very, very sensitive to water. So what happened in step 4 is, well, you can see that the benzene ring is gone, and you get a cyclohexane ring. So that's why it's called cyclohexyl methanol. And yeah, we can be thinking about all these reagent and conditions now. So this is step 1, and this is step 2, step 3, and this is step 4. Okay, so in step 1, this is a Friedel-Crafts alkylations. How in the world do I get this electrophile? So to get the electrophile, I can be thinking about CH2 CH3 Cl. Either that, or you can write CH3 CH2Cl, doesn't matter, it's the same thing. And I need AlCO3 catalyst, just like what I had done in the previous part A. So this and this will take away the Cl because this is the Lewis acid catalyst. It's an electron pair acceptor. So what happened there is the AlCO3 plus the CH3 CH2Cl. You're gonna get AlCl4 minus. So this is a tetrahedral shape because the aluminium has got 4 bond pair and 0 lone pair, and you will happily get your electrophile. This is your electrophile, and it's the exact same mechanism from the last question, electrophilic addition, except this time your benzene is like taking the carbon rather than a bromine. This is not asked by the question. The question actually starts by asking you identify a reagent and a catalyst. So your reagent is going to be CH3 CH2Cl. Your catalyst is going to be AlCO3, which is just a Lewis acid catalyst, or we say that it's an electron pair acceptor, because, well, you got an empty orbital on the aluminium since it's only got 6 electrons. After it share 3 electrons with the 3 of the chlorine, you only have incomplete outer shell. So the next part of the question, so what is structure A? We already told you just now that you are in alkaline environment, so do not draw an acid if you're in alkaline environment. It's going to be deprotonated. We don't know the cation because they don't say NaOH or KOH, so do not go and draw the cation. So just the benzoate, this is called benzoate. You can draw like this, or you can draw CO2 minus. Okay, so the name is called benzoate. You can't just put down the name because they say draw. Draw means draw. This is name. Moving to the next part of the question. So identify suitable reagents for step 3 and step 4. So step 3 just now was the reduction of this species to give you primary alcohol. Primary alcohol because the carbon with the OH is bonded to one other carbon. This is primary alcohol. The carbon with the OH is bonded to one other carbon. This is primary alcohol. So there is reduction there, and therefore I need a reducing agent in step 3, LiAlH4. I guess condition is not really required, but I often just put them together, LiAlH4 in dry ether. Ether is just a solvent, very, very volatile, very, very flammable, okay? So step 4 is when you lose the benzene ring and you add hydrogen across each of the carbons on the benzene ring, and you get an alkane, you get a cycloalkane. This happens under intense pressure, very, very high pressure, very high temperature. You also need nickel catalyst, and this is going to be hydrogen gas and nickel catalyst. You do not write down this one without mentioning catalyst because it's not a reactant, it's simply a catalyst. In the last part of the question is for 1 mark. They want you to work out carbon-13 NMR. So carbon-13 NMR means you are looking for the number of different carbon. I think it's important that I actually rub that out. Okay, so now I'm going to highlight in let's say brown color how many different carbon is there. All right, so if you can see, there's a planar symmetry there. So my diagram is not the best in the world, but you can see that because this side and this side are the same, this side and this side are the same. This side is a CH2, this side is a CH with an alkyl group, so this and this are different. So you got 1 carbon, 2 carbon, 3 carbon, 4 carbon, 5 carbon. So 5 different carbon because these and these are the same, these and these are the same, but these and these are not the same. Okay, so 1, 2, 3, 4, 5. There are 5 different carbon, and therefore you will see 5 peaks in the carbon-13 NMR of that cyclohexylmethanol. So that's the end of that 10 mark questions. And then in the next part of the question 9, this brand new question is again about NMR, but they are asking quite a lot of proton NMR. So first of all, they say proton NMR. So this one refer to proton. They say in CdCl3, so this is called deuterated solvent. This is called deuterated solvent. This specifically is deuterated chloroform. You want it to be deuterated. Deuterated means is actually isotope of hydrogen. Isotope of hydrogen. So they have the same proton or atomic number, but different mass number because they have different number of neutrons. So this is deuterium. It will not appear in the proton NMR. That's why we use deuterated solvent in our proton NMR, so that they will not interfere. They will not affect whatever peaks that we are supposed to see in our substance that we want to identify, which is this E, and it's C9H10O2. So that's the molecular formula of it. What do we know? Explain why CdCl3 is used as a solvent. Well, CdCl3, as I mentioned just now, the D is the deuterium, it's not a proton. So CHCl3 contain protons. Because the proton meaning 1,1H, so it's just hydrogen 1, we call it. We pronounce it as hydrogen 1 of the protons. In the CdCl3, nope, in the CHCl3 will appear in the proton NMR, but not the CdCl3, which does not contain proton. Therefore, it will not appear in the proton NMR. Somewhere along this line where this one will not appear in the proton NMR, but if you use CHCl3, the hydrogen there is a proton, and therefore it will appear in the proton NMR. Part B is about TMS. So TMS stands for tetramethyl-silane. So it's basically used as a reference standard. In fact, that's the answer. I'll just show you what I'm trying to say here. So it's actually a tetrahedral molecule. So silicon is just below carbon in the periodic table. So it's a 4 bond pair because you got 4 sigma bond around the silicon. And then it's 0 lone pair. So this is a tetrahedral 109 degree. It's a silicon sp3 hybridization. So what is important is all the carbon there have the same environment, and all the hydrogen there have the same environment as well. So what you will see is you will just see one giant peak at 0.0 ppm, that's parts per million ppm, at 0.0, because they are all identical. So that's why I put them all the same pink color there. All the carbon are also identical because you are in a tetrahedral geometry and they're exactly the same. Okay, so we use this as a reference standard, or just as a reference solvent. Oh, sorry, it's not a solvent, sorry. It's used as a reference standard, okay? Just for that 1 mark there, it's reference standard. We need something that we can always, go back to and say, this is 0.0, so everything is, measured or recorded relative to that reference standard. Part C, so compound E is hydrolyzed, so they use this term, hydrolysis. They say hydrolyze. They say hot NaOH, so this is in basic condition. So this is basic, or these alkaline conditions. You get 2 organic product, one of which is ethanol, but you don't know about this one. Okay, so you do get ethanol. Do we have any other information? Well, we have the molecular formula, which was C9H10O2. So if you have ethanol, so you are still missing 1 oxygen, and you don't have nitrogen. So this thing has no nitrogen. No nitrogen. So it is not nitrile. It is not amide. But it's got oxygen and it can be hydrolyzed. We talk about hydrolysis of nitrile, hydrolysis of amide. We also talk about hydrolysis of ester. There's an AS concept. So that means all of this information combined, therefore, E is an ester, which means the missing product is a carboxylic acid. Hang on, not a carboxylic acid, because you are in basic condition. So this must be carboxylate anion, okay, because you are in alkaline, or you are in basic condition because you have just done base hydrolysis, so you don't get the carboxylic acid. Okay, what else do they want? They want name the functional group E. Well, I've just done that, so that all points to E is an ester functional group. Name the functional group, not name the compound. All right. So the next part of the question is D part 1. So they say describe and explain. So there are 2 bits to that question. They want you to, it's 2 marks. So first of all, the splitting at 1.4. The splitting at 1.4 from your diagram, as you could see, is a triplet. A triplet would be 1:2:1 intensity. Because when you have a triplet, it will be 1:2:1. This is to do with intensity, and then the value itself has ppm, and you read it from the middle thing. Okay, from the middle thing is around 1.5 ppm. So what do we know there? Okay, so there is there's that confusion of like, where should you read from? You read from the middle of the peak, and it's 1.5 ppm. That's pretty low. So it's usually referring to a CH, well, depends on how many hydrogen is there. So there's a number associated on top, and this number is not the intensity. This number on top is what you call the oops, I don't want that. Do I want that? Yeah, this one is fine. So this number on top is called the integrated ratio. Sometimes they call it the integral. They tell you the number of hydrogens, well, the number of protons in that environment. So if you sum up all the number on top, you get 3 on the far right, and you get 2, and you get 5. So 3 plus 2 plus 5 give you 10, because the molecular formula of the compound is C9H10O2. You get 10 hydrogen altogether. So all the hydrogen, all the protons will appear in the proton NMR. Okay, so these are integrated ratio. So this triplet, this is what you see as a result of coupling to your neighbor. But how many protons do you have? What is the reason for it? Okay, So what happened that is, it is a CH3 next to a CH2. Okay, so this is where you are. This is where you are. But then you see a triplet, not because of this, because you are next to a CH2. Triplet mean 3 lines. 3 lines. You get 3 lines because n plus 2. How many neighboring protons do you have? Okay, sorry, n plus 1. I beg your pardon. So how many neighboring protons you must have? Plus 1 will give you how many lines you see in your NMR. You get 3 lines because you have 2 neighboring protons. That means you're next to a CH2. Okay, it's about where are you, how many protons you have where you are. This is where you are. The splitting is due to your neighbor. You have 2 neighboring protons, and therefore 2 plus 1 will give you 3 lines. So it's a triplet. All right, next to the CH2, therefore the CH3 sees 2 neighboring protons. You can say sees 2 neighboring protons, or you can see has 2 neighboring protons. Is entirely up to you. All right, so there's the first bit, and the second bit, the delta equal to 4.3. If you look next at the 4.3, you will see that there's a that, and then there's that, and then there's that. You try to read from the one in between, and the middle value is around 4.3, give or take, around 4.3 ppm. And there are 4 lines altogether. As you could see, there are, well, it's probably better on your paper, 1, 2, 3, 4. This is what you call a quartet. It's Quartet. And the reason for it, so if you look at the integral on top, you have a 2. You have a 2, and you suspect that it's this CH2. So it is a CH2 next to a, you got 4 lines because you have 3 neighboring protons. That is because you're next to a CH3. So next to a CH3, therefore the CH2 has 3 neighboring protons. Because you have 3 neighboring protons, then you will see 3 plus 1 line. That's why you see a quartet, which is 4 lines. But where are you? You are a CH2. That's why the integral, or the number given on top of that thing, the integral refers to how many protons do you have in that particular environment. Okay, so make sure you can read NMR data very, very well. On to the next part of the question. So D part 2. So they say there are 5 protons. There are 5 protons around delta equal to 7.0 to 8.5 ppm. So somewhere along this line, if you look at the data booklet for NMR data, this one should tell you straight away, these are aromatic protons, or you will say protons on the benzene ring. Aromatic protons means protons on the benzene ring. Okay, so they are saying the exact same thing. So you could just say either one, or you could say both of them. They will be repetitive, but they're exactly saying the same thing. Aromatic protons on the benzene ring. Okay, so now that we know that there is a benzene ring, we know there's a benzene ring, we know there's ethanol, because earlier in the question we were told that when you do hydrolysis in hot alkali or hot base, you get ethanol, and you get this carboxylate because you're in the presence of base, otherwise it will be an acid. We know it's an ester, so we need to identify this acid, and this acid comes from E, and there's no benzene ring in it, but E is the ester, and they have benzene ring because of this thing here. So we know we must have something with benzene ring, and it must be the carboxylate acid. So benzene ring has carboxylate acid. And what else do we know? We know this is 2 carbon, and we know that E, if you look at the formula of E earlier, it was C9H10O2. What else can I say to you? Why don't I just move these all the way down there, and then we can discuss on a brand new page without worrying about space. Okay, what else? We were going backward actually, so if I actually move E there, so there was the hydrolysis of the ester, and then I get ethanol, and I get benzene ring. So if I know my ethanol is C2H5OH. And don't forget that this is molecular formula of the ester. When you have alcohol plus carboxylic acid and you form ester, you will have to add water. So if I just balance the equation by adding water as well. So there's 2 carbons, so this must be 7 carbon. There is 10 plus 2 is 12 hydrogen. 12 minus 6 is going to be 6. And I've got O2 and O3. That means I will have O2. Okay, the reason I'm adding water here is because alcohol plus carboxylic acid, when they form ester, they will kick out a small molecule called water, or sometimes HCl depending on the reaction. But going this way is condensation, going this way is called hydrolysis. All of these are in the AS, identifying type of reaction. So condensation is actually an O-level or IGCSE concept, which you have done, condensation polymerization, and you're revisiting it again in AS as well as A2. Okay, so what else do we know? This one, you got to think about the NMR data. So it's 1 mark only for what is this ester E. What is ester E? All right, we know that. What else do we know? We know from the NMR data, we have a CH3 and a CH2. We know we have a CH3 and a CH2, and that comes from the alcohol, CH3, CH2OH, and we don't have any other protons, so what can I say? E is, well, CH3, CH2, and that is the alcohol, and then I have an ester, and I have a benzene ring. The benzene is 6 carbon plus 1 is 7 carbon, and there's 5 hydrogen there. As you saw earlier, there was 5 hydrogen integrated to 5 protons between 7 to 8.5 ppm. That's to do with the protons on the benzene ring. And you have CH3 and CH2. There's a result of the bit on the alcohol. If you try and fragment this thing here, you can hopefully see that you get CH3, CH2OH, and you get COOH, and what you actually lose is going to be the OH from the acid and the H from the alcohol, and then you will form the ester while kicking out H2O. Okay, so all this is probably not required, but all this is just part of the thinking process in order to get the structure of E, which is the ester there. Okay, hopefully that makes sense there. Probably just move down my answer over there. Excuse me. Alright, so we are down to the last 2 marks of the question. So part E. So they're given us this mass spectrum. So mass spectrum is all about fragmentation. Fragmentation means you just chop them up. So it's a mass of a charge. So what is very important is it's a mass of a charge on the x-axis. So anything which is not charged, you will not see in the mass spectrum. Okay, so the number you see is a result of, something electrons having been knocked out. That's why it has a plus charge. Everything in the mass spec has a plus charge. So 29 from here, very obvious, this thing are going to be big. C6H5 is a very special number. So 12 times 6 plus 5 is 77. So whenever you see 77, which is the next part of the question, there's your benzene ring, very obvious, C6H5. And this 29 is very obvious, the CH3, CH2. So 12 plus 3 times 1 plus 12 plus 2 times 1 is going to give you 29. So this thing is going to be CH3, CH2 with a plus. Just like that, with a plus, you need to identify and you need to make sure that they add up to 29 based on the structure that you have just suggested. Okay, so the next one that you have is 77, and this thing is going to be C6H5 as I mentioned earlier. So very straightforward, you get 2 things in your pocket, 2 marks in your pocket, and that's the end of that 9-mark question. Alright, moving on to the next question. I think this is the last question of the paper because, paper 4 is actually really long, isn't it? Anyway, so what do we need to do? So how we can see by identifying the pair of monomers, the fact that you have pair of monomers, then we can see what's going on. If I convert this into skeletal, because that's my most favorite thing to do in the world, to convert stuff into skeletal, and it will be a good practice for you as well to think about things in skeletal form. All right, so the fact that we have carboxylic acid as well as we have alcohol, so carboxylic acid will lose the OH and this will lose the H, and then they will condense this way and this way. So this is very clearly a condensation polymerization, and it will give you polyesters because these things condense together to give you esters. So that's very clearly polyester, therefore condensation polymerization. The other one, this is an acyl chloride, so I should probably draw acyl chloride properly. So there is an acyl chloride. So these things are what you call acyl chloride, and acyl chloride is an A2 concept. It's basically an equivalent of carboxylic acid, but it's a lot more reactive compared to carboxylic acid. Okay, a lot more reactive than carboxylic acid. And again, you have something that has two OH like that. So I can similarly, lose the Cl and lose the H there. Just like I lost the OH from the carboxylic acid, I can lose the Cl from acyl chloride, and I can polymerize that way and also polymerize that way. And here I will kick out HCl, whereas here I'll kick out H2O. In both cases, I add them together, but I also kick out small molecule, could be H2O, could also be HCl, because you learned that acyl chloride can form esters with alcohol, especially for phenol, because this is OH bonded to a benzene ring. You cannot form ester with phenol using carboxylic acid. You have to use the acyl chloride, which is the more reactive version, and that is why this is also condensation polymerization. But it's actually a very good revision to think that phenol cannot form ester unless you have acyl chloride. Now to the other one, so you have CH3, CHCF2. The fact that that is like that, it actually should tell you that you actually have alkene there. So what actually happens is you have CF2 and you have CH and a CH3. So you have two groups that are the same on one carbon of the carbon-carbon double bond. So there's no cis trans at all, because even though you have double bond, carbon-carbon double bond, but you have two groups that are the same atom or same groups of atoms on one carbon of the carbon-carbon double bond. So no cis and trans there. But the other compound that they are telling you is this thing, CH3, CH, CH2. So again, no cis and trans there. That is not the idea of this question. The idea is you have carbon-carbon double bond and you have another carbon-carbon double bond. Doesn't matter if you have the same double bond or different double bond, they can add together. And when they add together, do they need to kick out anything? No, they do not, because they are not forming ester, they are not forming amide. So that's why these things are just addition polymerization. Okay, I know it's only 1 mark, but I've spent a bit longer to talk about what could be the potential scenario in a longer type of question where they actually ask you to draw, and you gotta imagine what are you losing if you don't practice in your past year paper practice, like trying to think about all the possible scenarios, what kind of question can possibly come out. Then unless you're doing a time practice, you should always elaborate on what else could the question be asking you. If you're doing a time practice paper, then the 2 hours obviously very precious. You want to just rush through the questions as if you would rush through in a real exam, making as little mistake as possible. But if you are doing this as part of revision, or you're not timing yourself, it's important that you actually cover as much as possible. The next one is 2-aminopropanoic acid. So this is actually, I think this is amino acid, but let me just draw it out. They can polymerize under suitable conditions. If we just draw it out, so you have 3 carbon, you have carboxylic acid 1, 2, and 3. You have 2 amino, so it's NH2. So yeah, this is an amino acid, because what you could see then is you could see a carbon and an NH2 and a CO2H and a R group and a H. The R group here is just a CH3. So I think it is called alanine, something like that. Anyway, doesn't matter, but the official name is called 2-amino. 2-amino, so this is amino group because it's the amine. So this is the amine, which is the basic group. sorry, I'm diverging away from the question for a little bit, but it's important that as we go through these, that you actually can pick up a couple of new, recapping basic format or basic concepts. So this is CH3, not CH2. They want you to draw 3 monomer residues, and you got to identify 1 repeat unit. So draw 3 monomers as well as identify 1 repeat unit. Let me move that to a new page so I will not be rushed for space at all. So they are not asking us to display the amide, but sometimes they do ask you to display the amide linkage. So here I'll really just display the amide linkage, and then apart from that I don't really care that much. You just continue, and then this is the R group, which is the CH3, this is the CO. So going from here to here, this is one repeat unit, because that is your original amino acid unit, a carbon, a H and a CH3, and then the NH2 and the CO2H, polymerized that way and polymerized that way. So I'm just going to repeat this entire unit, and I can just draw it like this, and then this will be CO, and then that is your another repeat unit, and then NH, and yeah, it just repeat itself really. So carbon and then CH3 there, and so on and so forth. So they just want you to draw 3 monomer units, so 1, 2 and 3 monomer units from the 2-amino propanoic acid, which is basically this amino acid, and they want you to label or identify 1 repeat unit. And because it's polymer, you gotta mention that, or you gotta draw. You cannot have a close end there. You cannot have CO2H because it's a polymer. You cannot have NH2 on this end. It's gotta continue. It's gotta have an open chain there. How about the next part of the question? They said draw 2 stereoisomers. So this is actually an AS question. It's to do with optical isomers. As you know, most amino acids, in fact all amino acids, have a chiral carbon, except for one particular amino acid where the R group is H, and that is glycine. All right, so this is a repeat drawing of what I have on top there. So hopefully you can see that this carbon is chiral because this chiral carbon is bonded to 1, 2, 3 and 4 different groups. All amino acids are chiral. In fact, they have optical isomers, except when R equal to H, that is glycine. This is not glycine. They want you to state the type of isomerism. So the type of isomerism is going to be optical isomerism. So when you draw optical isomerism, you want to draw 3-dimensional drawings about the chiral carbon. So that's what I will draw now. So CH3, and then NH2, and then this is coming out towards you. This is pointing away from you. So there's CO2H. And then you always try and draw like a mirror image there, and that is when you start to put in the point first. This goes to this. So one of the things that some students have done is they thought that you have to actually write H3C instead of CH3. Well, this is a single bond. Each of the carbon to the hydrogen is a single bond. You can rotate about single bond easily. So whether you write H3C or CH3 is the same because you can rotate about single bond. And then this thing, the CO2H will mirror itself onto CO2H. That is the idea about mirror images. So one of the difficult thing about writing CO2H there is that you have to write CO2H like this, because if you write somewhere else, then it might not read as nicely as it is. So sometimes what people do is you can write CO2H there, and then you have H there, then it's a lot easier to read, right? So it's really entirely up to you, okay? Oops, I think I did a mistake. So this is pointing this way, so I have to draw that pointing that way and that pointing that way. I think I could do a much better job like that. So that will be the H, that will be the NH2. In reality, it does not matter where you put the 4 groups, as long as you have 4 of that CH3, CO2H, H, and NH2. Doesn't matter where you put them. If you don't like the CO2H on this or on that, you can put the CO2H there and you can put the CH3 there. It's entirely up to you. But what you must do correctly is you must mirror your stuff correctly, because there are non-superimposable mirror images. That's the very definition of optical isomerism.
Basically, you have a chiral carbon, therefore you get optical isomers that are defined as non-superimposable. These are your AS definition. They can and they will ask you when you least expect them to in paper 4. Non-superimposable mirror images of each other, and it comes as a courtesy of having a chiral carbon, a carbon bonded to 4 different atoms or 4 different groups. On to the next part of the question, and this is getting towards the end of the paper now. So they said this is the skeletal formula of compound Y. This looks weird. I don't know, I always hate drawing these this triangle thing. So these things are what we call epoxide actually. So when you have oxygen in a 3-member ring, it's called an epoxide, where oxygen is bonded to 2 carbon in a triangle, or in a not a triangle, but ring strand. Remember that there are 2 hydrogen here, so it's a carbon sp3, carbon sp3, carbon sp3, and carbon sp3. Carbon sp3 likes to be 109 degree tetrahedral. Here it's forced to be 60 degree, which means it really doesn't want to remain like this. It wants to open up the ring. Okay, it wants to open up the ring. And this is a case study because it's stated in the syllabus. It's an adhesive. Adhesive is like super glue, so it sticks together. It sticks together really well. I don't know why that thing doesn't write that well anymore. So super glue, so they stick really well. So the name for this type of stuff is called epoxy resin. All right. Nope, that didn't write properly either. So the hardener is a diamine. So diamine. So they say you have a diamine. Diamine means di meaning 2, amine means you have NH2 group. So what do we have? Draw the structural formula of a compound. They say a compound. They don't say the compound. So a meaning anyone. But remember, you gotta have 2 times NH2. So, and what else? You have alkyl chain. Alkyl chain meaning in between the terminal. So I don't think there is one particular answer to it, but if you can imagine that one of your other case studies, so this is not asked in this question, but one of your polymer case study is nylon 66. So it's to do with when you have CH2 and you got 6 and then you got NH2 and NH2. This thing is what you call the spacer linker. Spacer linker, they fill up the space in between. It just happened to be 6 because it's 6 carbon there. And of course nylon 66 is a polyamide. It's a synthetic polyamide. You've got the diamine. You also need the dicarboxylic acid. So dicarboxylic acid contains carboxylic acid at the end. I don't want the square diagram, which is your O-level or GCSE or IGCSE. So because I have a COOH at the end, so there's 1 carbon, 2 carbon, so I just need 4 there. So that is your spacer linker there in between as well. Oops, sorry about that. Anyway, so our spacer linker here is alkyl chain. They just say it's a diamine, so they don't say the compound, they say a compound. So I think I should be able to get away with just H2N and then CH26NH2, which is the monomer that I use to form nylon 66. And I can apply it to these particular questions on epoxy resin that they want me to do on a diamine with an alkyl chain. They don't tell me how many alkyl chain there are, but the amine group are not bonded to the same carbon. So meaning to say anything which is more than 1 carbon will be okay. The two amine groups are not bonded to the same carbon. So if you have only 1 carbon, the 2 amine group will be bonded to the same carbon. So anything as long as it's not 1 carbon, I think 2 carbon, 3 carbon, 4 carbon, 5 carbon, 6 carbon will be okay. But obviously you don't want your monomer to have 1000 carbon, for example, then it probably doesn't make that much sense. Alright, for that 1 mark question is kind of suggestion questions, and that's the end of that 8 mark question. So yeah, I mean, this question is done. In fact, this paper is done, so I'm done with this paper 4 finally. Okay, so it's been a long paper as usual. So paper 4 is always really long, and yeah, I hope you found my explanations, the way I think through questions, a little bit of extra information here and there, because I'm not just doing the paper. Hopefully, as you revise with my tutorial video, you actually learn a couple of new things along the way and a good recap of your AS. If you found you missed something, then it's good to actually recap back your AS concepts before you just keep on doing more and more paper. Okay, so thank you for watching, and do click the button on the bottom right to subscribe to the channel. So the button on the bottom right should be bottom right hand side where I'm circling right now. It should appear as a pop out, so do subscribe to the channel, and please share the channel widely with all your friends, chat group, juniors, seniors, and other people you think the channel can help them. Okay, and yeah, follow me at ptet.chemistry. That is ptet.chemistry on Instagram, Facebook, and Twitter, to get connected. And yeah, I mean, this is a new restructured format of tutorials, so it's always going to take a while before I go back to the glory of good old days, but eventually, sooner rather than later, eventually I have enough content to build up a library from which I can get more topical content out from. Okay, thank you for your support, and see you in the next tutorial video.